In the distant universe, more than 12 billion light-years away from us, shines a cosmic beacon of almost unimaginable power, an object so radiant that it dwarfs the light of our entire Milky Way galaxy by a factor of hundreds of thousands. This is the quasar J05294351, currently recognized as the brightest and most luminous single object ever discovered in the observable universe. We see it as it was when the cosmos was less than 2 billion years old, a mere teenager in cosmic terms. Despite its immense distance, its light has traveled across the expanding void to reach our telescopes, carrying with it a story of extreme physics, rapid growth, and the violent dawn of galactic structures. This quasar emits light with a luminosity equivalent to more than 500 trillion suns, a torrent of energy so immense that it pushes the very limits of our physical understanding. At the heart of this dazzling celestial powerhouse resides a supermassive black hole, a gravitational monster that is growing at an extraordinary and terrifying rate. Astronomers estimate that this black hole is consuming matter equivalent to the mass of our sun every single day. This ferocious accretion rate is what fuels the quasar's incredible brilliance. The black hole's mass is already estimated to be in the range of tens of billions of times that of our sun. Yet it continues to feed furiously, converting the matter that falls into it into a flood of radiation with record-breaking efficiency. The source of this immense power is a vast and turbulent accretion disk surrounding the black hole. This is a swirling vortex of gas, dust, and shredded stars, likely spanning several light-years in diameter, heated to millions of degrees as it spirals inward. The intense friction and magnetic turbulence within this disk, which is rotating at relativistic speeds, transform the gravitational potential energy of the infalling matter into an astonishing outpouring of high-energy light, a flood of radiation that jets out from the quasar's core in all directions, making it visible across a vast swath of the observable universe. What makes J05294351 especially fascinating for astrophysicists is how its extreme brightness challenges our classical assumptions about the physics of black hole accretion. There is a theoretical maximum luminosity that an object like a quasar can achieve, known as the Eddington limit. This limit represents the point at which the outward pressure of the radiation produced by the accretion disk exactly balances the inward pull of the black hole's gravity on the surrounding gas. If an object were to shine brighter than this limit, the intense radiation pressure should blow away its own fuel supply, effectively shutting down the accretion process. Somehow, this quasar seems to be circumventing these restrictions, shining at a luminosity that appears to be super Eddington. This paradox raises profound new questions about the physics of extreme gravity environments, about the geometry of accretion disks, about the role of magnetic fields, and even about the possibility of subtle changes in physical laws under such extreme conditions. The unprecedented luminosity of J05294351 makes it an invaluable laboratory for testing and refining our astrophysical theories about the growth of supermassive black holes in the early universe and the fundamental physics of matter-energy conversion near an event horizon. It represents a cosmic scenario that pushes our standard accretion models to their theoretical breaking point, forcing astronomers to either refine their classical assumptions or to consider entirely new and more exotic physical mechanisms. The apparent super Eddington luminosity of this quasar implies the existence of unusual physical conditions. One possibility is that the radiation is being emitted anisotropically, meaning it is not shining equally in all directions. If the quasar is producing powerful, beamed jets of radiation that happen to be pointed towards us, it could appear much brighter than it actually is. Another, and perhaps more likely, possibility is that the accretion process itself is different from our standard models. The accretion disk might be geometrically thick and clumpy, rather than thin and uniform, or it might be supported by incredibly strong magnetic fields and turbulent viscosity that allow matter to flow inward at a much higher rate than predicted by classical theory. Detailed spectroscopic studies of the light from J05294351 have revealed prominent broad emission lines, which are the characteristic signature of clouds of extraordinarily hot ionized gas orbiting the central black hole at incredible speeds, approaching several thousand kilometers per second. The analysis of these emission lines provides us with critical clues about the chemical composition of the gas in the early universe. The surprising presence of a high abundance of heavy elements, or metals, such as iron, magnesium, and silicon, in this ancient gas implies that the processes of stellar nucleosynthesis, the creation of heavy elements inside stars, must have occurred remarkably quickly after the Big Bang, much earlier and more efficiently than many traditional models of galaxy formation would suggest. This quasar is telling us that the first generations of stars in its host galaxy must have lived fast and died young, seeding their environment with the building blocks of future stars and planets. Furthermore, the intense and relentless flood of ultraviolet and X-ray radiation emanating from J0529-4351 has a profound and violent impact on its surrounding galactic environment. This phenomenon, known as quasar feedback, occurs when powerful radiative winds and kinetic jets, driven by the black hole's accretion disk, blast through the host galaxy, expelling vast quantities of gas at tremendous speeds. This process can effectively shut down or severely disrupt the process of star formation in the galaxy, and can even influence the evolution of the galaxy on the largest scales. This quasar is not just a passive beacon, it is an active and powerful engine of galactic transformation. Astronomers also use incredibly bright and distant quasars like J05294351 as cosmological lighthouses, powerful tools for probing the otherwise invisible structures that lie in the vast expanses of intergalactic space between us and them. The extremely bright light emitted by this object has been traversing the universe for over 12 billion years. On its long journey to us, it has passed through countless clouds of primordial gas, the vast, wispy filaments of the cosmic web, and the massive, invisible halos of dark matter that surround distant galaxies. Each of these intervening structures absorbs a tiny fraction of the quasar's light at specific characteristic wavelengths. As a result, the spectrum of the quasar's light that reaches our telescopes is imprinted with a forest of absorption lines, known as the Lyman alpha forest. This forest is a cosmic chronicle, a detailed record of the distribution and properties of baryonic matter and the process of cosmic reionization at different epochs in the universe's history. Additionally, J05294351 and other luminous quasars help astronomers to measure cosmological distances and to refine the fundamental parameters of our cosmological model, such as the Hubble constant, which describes the current expansion rate of the universe and the density of dark energy. By studying the intrinsic flickering variability of the quasar's brightness, astronomers can use a technique called reverberation mapping to make precise timing measurements, which can yield independent constraints on these fundamental cosmological constants, helping to resolve some of the current tensions in our understanding of the universe's expansion. Further investigation of this extraordinary object using the next generation of powerful telescopes, including the James Webb Space Telescope, the ground-based extremely large telescope, and future space-based X-ray observatories, will likely provide even more precise and revealing data. These new facilities promise to give us our first deep insights into the quasar's host galaxy, which is currently completely outshone and obscured by the intense glare of the central engine, as well as detailed maps of the immediate environment surrounding the supermassive black hole. revealing the dynamics of the gas flows that are feeding this cosmic monster. Through the subtle effects of gravitational lensing, astronomers might also be able to use the exceptional brightness of J00529435 to uncover previously undetectable structures that lie along our line of sight, including small-scale clumps of dark matter or hidden dwarf galaxies. Such lensing phenomena, magnified and illuminated by the quasar's light, could help astronomers to resolve some of the current tensions in our theories of galaxy formation and our models of the distribution of dark matter. J05229435 thus serves as more than just an extraordinary cosmic beacon. It is also a unique astrophysical laboratory, a place where we can test the predictions of Einstein's general theory of relativity in the ultra-strong gravitational fields that exist near a supermassive black hole. For example, detailed studies of the shape of the iron K-alpha emission lines, which are produced in the innermost regions of the accretion disk, can reveal the effects of frame dragging, a phenomenon predicted by general relativity, where the rotating mass of the black hole literally twists the fabric of space-time around with it. As our observations become increasingly precise, J05294351 could ultimately enable us to test even more speculative physical theories, including various models of quantum gravity or alternative theories that attempt to resolve the paradoxes of black hole singularities and the loss of information. Such research could eventually help us to bridge the long-standing gap between classical astrophysics, general relativity, and the strange world of quantum mechanics. The ongoing studies of this extraordinarily luminous quasar have profound implications that extend even to our most fundamental cosmological enigmas, including the theory of cosmic inflation and the process of early structure formation. The sheer, overwhelming intensity of its radiation not only reveals the physical processes that occur in the most extreme gravitational and energetic regimes in the universe, but it also allows for incredibly high-resolution spectroscopy and polarimetry. These techniques provide us with a unique and unprecedented view into the geometry, the dynamics, and the magnetic environment of the region immediately surrounding this supermassive black hole, a region that is ordinarily far too small and too distant to be resolved. An intriguing and important aspect of such hyperluminous quasars is the potential role they played in the process of cosmic reionization. This was a crucial epoch in the early history of the universe, from about 400 million to 1 billion years after the Big Bang, when the neutral hydrogen gas that filled the cosmos became ionized by the first sources of intense ultraviolet radiation. The immense and powerful flood of ultraviolet and X-ray photons from a celestial beacon like J05294351 indicates that similar, though perhaps less extreme, super-bright quasars, while individually rare, may have collectively contributed significantly to this reionization process, helping to accelerate the transition of the universe from a neutral, opaque state to the transparent and ionized cosmos that we observe today. Furthermore, the exceptional brightness of this quasar allows astronomers to probe and measure very subtle relativistic phenomena, effects that are predicted by theory but are incredibly difficult to observe elsewhere. One such example is gravitational redshift, a phenomenon where photons that are emitted from deep within the quasar's powerful gravitational well lose a small amount of their energy as they climb out and escape into space. This loss of energy manifests as a slight shift in their wavelength toward the red end of the spectrum. Precise measurements of this redshift, by comparing the observed wavelengths of emission lines with their known rest frame wavelengths, could lead to direct and powerful tests of the predictions of general relativity in the ultra-strong gravitational field regime, a place where the theory has never been so rigorously tested. The study of the quasars' spectral variability over time also yields critical astrophysical insights. Variations in its luminosity and in the shape and intensity of its spectral lines can reflect the presence of waves of instability or large-scale turbulence propagating through the accretion disk. These fluctuations may be linked to a key theoretical mechanism known as the magnetorotational instability, or MRI, which is thought to be the primary process that governs the transport of angular momentum in accretion disks, allowing matter to overcome its orbital inertia and fall into the black hole. By examining how these fluctuations propagate through the disk over periods of months and years, astronomers can gain a deeper and more detailed insight into the complex physics that underlies the structure of accretion disks and their long-term stability. From a more practical observational standpoint, the sheer, overwhelming brightness of such luminous quasars makes them ideal calibration points for our new and most advanced telescope systems. They can be used to help refine and calibrate our observational methods across the entire electromagnetic spectrum, from the far infrared to the highest energy gamma rays. Their incredible clarity and relative consistency facilitate the characterization of our instruments and the calibration of our wavelength measurements, thereby broadly contributing to significant improvements in all of observational astrophysics. They are, in a sense, the ultimate cosmic standard lamps. Moreover, these hyperluminous objects might even indirectly support the detection of gravitational waves from the mergers of distant supermassive black hole binaries. The intense radiation emitted by these quasars could ionize or stimulate the gas in the vast regions of intergalactic space, forming environments that might amplify the subtle signals of passing gravitational waves or produce detectable electromagnetic counterparts to these otherwise invisible events. The quasar's powerful and complex magnetic environment also invites extensive and detailed investigation. The high-energy jets and powerful outflows that emanate from its accretion disk suggest the presence of extraordinarily strong and well-organized magnetic fields, which are formed by the complex dynamics of the relativistic plasma swirling around the black hole. By studying the polarization properties of the light emitted by the quasar, astronomers can map the structure and orientation of these magnetic fields, providing invaluable clues about the mechanisms of magnetic field generation and the crucial role that these magnetically driven winds play in the extraction of energy from the accretion disk near the black hole's event horizon. Chemically, the detailed spectral analysis of hyperluminous quasars frequently reveals a surprisingly high abundance of heavy elements, such as iron, magnesium, and silicon. This indicates a rapid and efficient process of stellar nucleosynthesis in the quasar's host galaxy. The presence of such a high degree of metal enrichment, occurring within the first few billion years of the universe's existence, forces astronomers to reconsider the timescales and the processes that were involved in the formation of the first stars, the first supernova events, and the overall chemical evolution of the interstellar medium in the early cosmos. Finally, these ultra-bright quasars serve as invaluable cosmic distance markers, helping us to refine our understanding of the expansion of the universe and the mysterious nature of the cosmological constant, or dark energy. By tracking the correlated fluctuations in the quasar's luminosity across different wavelengths, astronomers can establish a new and more precise type of standard candle, which can help to resolve the current discrepancies between the measurements of the universe's expansion rate that are derived from the cosmic microwave background and those that are obtained from more local distance indicators. Thus, beyond their intrinsic and profound fascination, quasars of such unparalleled and astonishing brightness are fundamentally shaping our understanding of physics, cosmology, and the evolution of galaxies, offering astronomers an extraordinary and irreplaceable window into the most energetic, the most dynamic, and the most enigmatic processes in the entire universe. The discovery and detailed observation of this extraordinary quasar also contribute significantly to our models of how supermassive black holes form in the first place. The extreme conditions that are required for such a massive object to grow so quickly within the limited time frame of the early universe force astronomers to explore unconventional and more exotic mechanisms, such as the direct collapse of massive primordial gas clouds, the rapid mergers of a chain of primordial black holes, or even scenarios involving the gravitational influence of dark matter halos seeding a process of rapid and efficient black hole accretion. Furthermore, advanced computer simulations of the accretion disks around such luminous quasars indicate that complex relativistic effects, such as photon trapping, may become dominant in these extreme regimes. In this phenomenon, the radiation that is produced deep within the accretion disk, close to the black hole, struggles to escape the immense gravitational pull. This trapping of photons could help to explain how these objects are able to surpass the classical Eddington limit by reducing the outward push of the radiation pressure and allowing matter to continue flowing inward at these unprecedented and ferocious rates. Moreover, the quasar's existence in the early universe, close to the cosmic dark ages, an era when the first galaxies and quasars were just beginning to emerge, makes it a crucial laboratory for understanding the conditions that existed shortly after the Big Bang. Its intense emissions serve as a powerful backlight, illuminating the otherwise invisible clouds of intergalactic gas and enabling astronomers to reconstruct how the very earliest galaxies assembled themselves from the primordial hydrogen and helium gas clouds into the structured, star-forming systems that would eventually populate the cosmos. In addition, the observations of these incredibly bright objects are enhancing our theoretical models of how cosmic dust is formed and how it survives, despite the incredibly intense and harsh radiation environment that should, in theory, evaporate and destroy dust grains very quickly. These hyperluminous quasars surprisingly host significant reservoirs of dust, investigating how this dust is able to survive and even thrive. In such close proximity to these extremely luminous accretion disks is challenging our current theories of dust grain chemistry, of radiation shielding, and of the processes of grain growth in turbulent and highly irradiated regions of space. Spectropolarimetric studies, which measure the polarization of the light from these objects, have also begun to unravel the complex geometry of these energetic systems. These measurements of polarized light allow astronomers to map the orientation of the accretion disks, the powerful jets, and the obscuring structures often referred to as dusty tori that are thought to surround supermassive black holes. Such detailed polarization maps can enhance our understanding of the intrinsic anisotropy in the radiation fields of these objects, which could be another key to explaining why some quasars are able to achieve such extreme brightness, seemingly in defiance of the theoretical luminosity limits. From an astronomical instrumentation perspective, the study of extremely luminous quasars is stimulating the development of new and innovative methods in fields like adaptive optics, which corrects for the blurring effects of Earth's atmosphere, interferometry, which combines the light from multiple telescopes to achieve higher resolution, and space-based telescopy, the ongoing efforts to resolve the fine structures surrounding these supermassive black holes, including measuring the sizes of their accretion disks or resolving their powerful jets with extremely high resolution, are fostering crucial technological advancements that will be essential for future missions, like the Laser Interferometer Space Antenna or the next generation of very long baseline interferometry networks. The cosmological implications of observing these distant and luminous quasars also extend to the burgeoning field of neutrino astronomy. The hyper-energetic accretion events that power these quasars are believed to produce significant fluxes of high-energy neutrinos through violent particle collisions that occur near the black hole's event horizon. Detecting the neutrinos that are associated with these distant quasars would open a completely new observational window into the fundamental astrophysical processes at play, allowing us to verify our theoretical models of particle acceleration and radiation physics at the most extreme energies. Gravitational lensing by these incredibly bright quasars also provides astrophysicists with a powerful means to probe the intervening structures of dark matter, which are completely invisible through traditional electromagnetic observations. The subtle microlensing of the quasar's light by smaller unseen objects that pass in front of it, such as isolated black holes or dense clusters of stars, becomes detectable thanks to the quasar's immense brightness. This can help to inform our models of the distribution of dark matter on subgalactic scales. Finally, the powerful radio and gamma-ray emissions that often accompany these ultra-bright quasars help us to refine our theoretical models of how relativistic jets are produced. Understanding the complex processes that are able to efficiently channel the immense energy from the accretion disk into tightly collimated relativistic jets involves a deep understanding of complex magneto-hydrodynamics and particle acceleration physics. The observational constraints that are derived from these quasars thus contribute to a broader and deeper knowledge of relativistic astrophysics, a field that is applicable to a wide range of diverse and enigmatic cosmic phenomena, from gamma-ray bursts to the active galactic nuclei that power the jets we see in many nearby galaxies. In summary, these exceptionally luminous and distant objects stand as invaluable and irreplaceable astrophysical laboratories. They challenge our existing theories. They inspire innovative new observational methodologies, and they dramatically enhance our understanding of fundamental physics, of cosmic evolution, and of the nature of the very early universe. Delving deeper into the realm of astrophysical theory, the existence of hyperluminous quasars like J05294351 compels researchers to re-evaluate some of the fundamental assumptions about the early universe, including the initial mass function, which describes the distribution of stellar masses at birth, and the overall rates of star formation in the primordial cosmos. The incredibly rapid accumulation of mass required to form these supermassive black holes so early in the universe's history necessitates either an unprecedentedly dense and gas-rich environment or significantly higher densities of massive stars, potentially indicating subtle shifts in the physics of the early universe or previously unknown and highly efficient mechanisms of star and black hole formation. Furthermore, the detailed physics of accretion disks under these extreme gravitational and radiative conditions remains a vibrant and active area of ongoing theoretical exploration. Current computer simulations indicate that the accretion disk around an ultra-bright quasar might transition into a state known as an advection-dominated accretion flow, or ADAF. In this state, a significant portion of the gravitational energy released by the inflowing matter is not radiated away as light, but is instead directly absorbed or advected by the black hole itself. Investigating the properties of ADAFs in such extreme contexts could uncover novel and important accretion dynamics and energy dissipation mechanisms, helping to close the theoretical gaps that exist between our classical, simpler accretion models and the more complex and realistic behaviors of relativistic disks. The study of the powerful quasar-induced winds also provides critical insight into the process of kinetic feedback, which is an essential ingredient in our modern cosmological simulations that dictates how galaxies evolve over time. In these hyper-energetic environments, the kinetic outflows, the vast streams of gas that are driven out of the galaxy by the intense radiation pressure from the quasar can transport heavy elements, or metals, and other enriched materials far out into the intergalactic medium. Understanding this process of galactic enrichment allows cosmologists to refine their numerical simulations that predict the distribution and evolution of metals on the largest cosmic scales, helping to illuminate the cosmic pathways through which the elements that are essential for life are dispersed across vast and empty cosmic distances. Moreover, these luminous quasars indirectly facilitate the study of large-scale cosmological structure, as the bright light emitted by these quasars travels across immense cosmological distances. The subtle distortions that are caused by the gravitational fields of the intervening galaxy clusters provide us with precise and powerful tests of Einstein's theory of general relativity on the largest possible scales. Such measurements can help to identify any potential discrepancies with the theory, or to confirm the predictions of alternative gravitational theories, offering astronomers critical empirical evidence that goes far beyond the local environments of our own solar system or galaxy. Additionally, quasars of such extraordinary and stable brightness can serve as ideal reference sources in the field of precision astrometry, which is the precise measurement of the positions and motions of cosmic objects. By tracking the minute positional shifts of these quasars over decades, astronomers can seek to detect very subtle relativistic phenomena, such as the effects of a background of low-frequency gravitational waves, the orbital motion of binary supermassive black holes, or the micro-lensing effects caused by unseen objects at extreme cosmological distances. These precise positional observations could lead to major breakthroughs in our understanding of the cosmic gravitational wave background and the evolution of the supermassive black hole binaries that are thought to be at the heart of many galaxies. The powerful ultraviolet and X-ray emissions from these quasars also have a profound influence on the chemistry of the intergalactic medium. The high-energy photons emitted by the quasar ionize the surrounding gas, fundamentally altering its chemical composition and its thermal structure. Detailed observations of the absorption lines from this gas allow astrophysicists to map the distribution of highly ionized elements like carbon, oxygen, and neon, thus shedding light on the temperature and density distribution of the diffuse cosmic gas that fills the space between galaxies. These are vital components in our cosmic simulations of structure formation and evolution. From a broader theoretical standpoint, the observed abundance of extremely bright quasars at high redshift poses some significant challenges for our standard models of cosmic inflation and the timelines of structure formation. Our standard cosmological simulations must either account for much earlier formation times for these large-scale structures or reconsider some of the fundamental assumptions about the nature of the initial density fluctuations that were present shortly after the Big Bang. Such insights could ultimately reshape the entire theoretical framework of our cosmological history. Furthermore, the detailed observations of these hyper-energetic quasars serve as invaluable laboratories for the study of plasma physics under extreme conditions, including processes like magnetic reconnection, which is a key mechanism in the acceleration of particles and the launching of powerful jets around compact objects. A detailed analysis of the patterns of emission variability and the polarization signatures of the light from these objects can provide crucial clues about how these complex magnetic processes unfold in the most extreme astrophysical environments, advancing our understanding of high-energy astrophysics and plasma dynamics in general. Finally, these luminous cosmic beacons offer us incredible opportunities for multidisciplinary studies that can involve nuclear physics, particle physics, and quantum field theory. The observations of intense gamma-ray flares, The potential detection of associated neutrino emissions and the study of the relativistic particle jets allow physicists to study the processes of particle acceleration, the effects of quantum electrodynamics in strong electromagnetic fields, and possibly even to probe for the existence of new physics, such as the signatures of actions or dark photons, which are hypothetical particles proposed by theories that go beyond the standard model of particle physics. Thus, beyond their intrinsic astronomical interest, these extraordinarily luminous quasars hold an immense potential for revolutionizing numerous branches of physics, fostering deeper and more profound insights into the most fundamental cosmological phenomena, the world of particle physics and the very earliest phases of our universe. The study of these exceptionally luminous quasars is also advancing our understanding of the complex instabilities that can arise in accretion disks that are dominated by radiation pressure. In such intense and extreme environments, the outward push of the radiation can exceed the inward pull of gas pressure by many orders of magnitude. This can trigger a range of powerful instabilities, such as thermal viscous instabilities or the so-called photon bubble instability. These phenomena can cause the accretion disk to fragment into dense, optically thick clumps, or can induce rapid and dramatic fluctuations in the quasar's luminosity and the overall structure of the disk, effects that are directly observable through precise and long-term photometric monitoring. Furthermore, a detailed analysis of the multi-wavelength emission patterns of these luminous quasars, from the lowest energy radio waves to the highest energy gamma rays, allows astronomers to build complex models of the interplay between different radiation mechanisms, such as synchrotron radiation, which is generated by relativistic electrons spiraling in powerful magnetic fields, and inverse Compton scattering, a process where low-energy photons gain a huge amount of energy through collisions with high-energy electrons. Studying how these different processes balance each other out in these extreme environments provides us with deeper insights into the mechanisms of particle acceleration and cooling under the most extreme astrophysical conditions. Hyperluminous quasars also provide us with critical observational constraints on the opacity of the intergalactic medium at very high redshifts. As the photons from these distant quasars traverse the vast cosmological distances to reach us, their interactions with the neutral hydrogen and helium that filled the early universe produce distinctive and powerful absorption features in their spectra, particularly the Gunn-Peterson trough, which are invaluable for dating the epoch of Ryanization with a high degree of precision. Thus, these quasars are crucial cosmic chronometers that help us to calibrate our cosmological models concerning the universe's historic transition from a neutral and opaque state to the ionized and transparent cosmos that we inhabit today. Additionally, the fact that these quasars, which are emitting such exceptional luminosities, are able to exist at all challenges our theoretical models of how cosmic dust survives in the universe. Standard theories would suggest that dust grains should be very rapidly destroyed by the intense and energetic photon fields that are produced by these objects. And yet, observations have shown that significant reservoirs of dust remain present in these extreme environments. Resolving this apparent paradox involves re-evaluating our understanding of the processes of dust grain growth, destruction, and radiation shielding, which could potentially lead to a major revision of our understanding of grain physics and the processes of chemical enrichment in the turbulent and highly irradiated regions of the early cosmos. Another intriguing area of research that is influenced by these powerful quasars is the study of starburst quasar interactions. Astronomers have long hypothesized that there is a complex feedback loop in which periods of rapid star formation, or starbursts, in the host galaxy provide the fuel for the central quasar, and the quasar, in turn, subsequently suppresses or regulates further star formation through its intense radiation-driven outflows of gas. By making detailed observations of the gas motions, the star formation rates, and the distribution of molecular gas in the regions immediately surrounding these hyper-energetic galactic nuclei, astronomers are able to refine their feedback models, helping to clarify the complex and co-evolutionary relationship that exists between galaxies and their central supermassive black holes. The extreme brightness of these distant quasars also enables astronomers to probe previously inaccessible cosmic epochs, most notably the epoch of first galaxies, the period when the very earliest galactic structures were just beginning to assemble. By using the light of these quasars as a powerful backlight, we can illuminate these early, faint galactic structures, providing us with insights into the nature of the primordial stellar populations, the so-called population 3 stars, the formation of the first galactic clusters, and the growth of dark matter halos at unprecedentedly early cosmic times. On the experimental frontier, the next generation of gravitational wave observatories, such as the Laser Interferometer Space Antenna, or LISA, aim to detect the low-frequency gravitational waves that are generated by the mergers of supermassive black holes, a process that is likely to involve these luminous quasars. By correlating the detection of these gravitational wave events with the electromagnetic signals from the quasars, we could confirm our models of how black holes grow, the dynamics of their accretion, and the scenarios of merger-driven galaxy evolution, a discovery that would profoundly influence the future of gravitational wave astronomy. Moreover, the study of these hyperluminous quasars is providing us with deep insight into the evolution of cosmic magnetic fields. Their strong and often polarized emissions indicate the presence of well-organized magnetic fields with extraordinary strengths that have a major influence on the dynamics of accretion, the collimation of jets, and the acceleration of particles. Understanding the origins and the evolution of these powerful magnetic fields is fundamental for building comprehensive models of galaxy formation and the process of magnetogenesis in the infant universe. In addition, the extraordinary radiation fields that are produced by these quasars are helping astrophysicists to test the predictions of quantum electrodynamics, or QED, in the presence of intense gravitational and magnetic fields. Exotic phenomena such as vacuum birefringence, a state where the vacuum itself is predicted to behave as a birefringent medium under extreme magnetic conditions, could become observable, allowing for unprecedented tests of the fundamental principles of physics. Finally, these hyper-energetic quasars indirectly support our cosmological studies of the propagation of cosmic rays and the search for the sources of high-energy neutrinos. The extreme particle acceleration processes and the immense energies that are inherent to these quasars make them ideal natural laboratories for the study of particle acceleration physics. They could potentially help us to identify the distant and mysterious sources of the ultra-high-energy cosmic rays and neutrinos that we detect here on Earth, thus uniting the fields of astrophysics and particle physics in a single, coherent observational framework. In this way, the study of these exceptionally luminous quasars is not only enriching our astrophysical theories, but also promises to answer some of the most profound and fundamental scientific questions about the nature of our universe. Connecting cosmology, fundamental physics, and the astrophysics of the early universe in a single, unified scientific narrative. The exploration of these enigmatic and radiant cosmic beacons is pushing the very limits of human knowledge, prompting us to ask deeper and more profound inquiries into the very nature of reality itself. Their extreme and almost impossible luminosity hints at the presence of unseen processes that may be lurking just beneath the surface of our observable physics, compelling scientists to consider novel and exotic mechanisms. Could these objects, shining brighter than entire clusters of galaxies, be subtle gateways to undiscovered physical laws or to cosmic realms that we have yet to comprehend? Perhaps the physics at play is tied to the mysterious nature of dark matter, dark energy, or even the existence of hidden extra dimensions of reality. Intrinsically, the immense gravitational pull of these quasars might also enable astronomers to one day test some of the more speculative but profound ideas in theoretical physics, such as the holographic principle, a theory which suggests that all of the information about our three-dimensional universe might be encoded on a distant two-dimensional boundary surface, like the event horizon of a black hole. The detailed observations of subtle quantum or gravitational phenomena in these incredibly intense environments could one day unlock the first clues about how space, time, and gravity intertwine at the deepest and most fundamental quantum scales, possibly bringing scientists closer to resolving some of the long-standing and deeply perplexing enigmas that surround the nature of black hole singularities. Furthermore, the extraordinary particle acceleration environments that are found near these luminous giants could shed new light on the enduring mysteries of high-energy cosmic rays, the sources of cosmic neutrinos, and the potential signatures of dark matter annihilation. Could the immediate vicinity of these quasars, a region of space that is bathed in intense radiation and powerful twisted magnetic fields, be a natural particle accelerator that is far more powerful than any human-made collider could ever hope to be? Could the subtle and as yet unexplained signals in their spectra, or in the fluxes of cosmic rays that we observe here on Earth, be hinting at interactions that involve new and undiscovered fundamental particles? Moreover, cosmologists have begun to speculate whether the distribution of these extremely luminous quasars in the early universe holds hidden clues about the process of cosmic inflation, the brief but explosive period of expansion that is thought to have occurred just moments after the Big Bang, a process that shaped the universe as we know it today. The subtle patterns that may be imprinted on the large-scale distribution of these ancient and brilliant quasars might provide us with the first direct observational signatures of the physics of inflation, offering crucial tests for theories that are currently limited to the realm of pure theoretical speculation. Astrobiologists, too, have begun to ponder the indirect and complex implications of these hyperluminous quasars for the possibility of life existing elsewhere in the universe. While their intense and powerful radiation would almost certainly sterilize any nearby planets, could their powerful galactic outflows be responsible for distributing the essential elements for life, such as carbon, oxygen, and phosphorus, across vast cosmic distances, effectively seeding distant galaxies with the necessary building blocks of life billions of years before our own Earth even formed? Are these extraordinarily bright and powerful objects, which are so paradoxically destructive at close range, actually vital and necessary participants in the grand cosmic chemical cycles that are essential for the universal emergence of life? Equally compelling is the potential to use these quasars as a new and more precise type of standard candle cosmic lighthouses whose predictable luminosity variations across vast cosmological distances could help us to refine our models of precision cosmology beyond their current capabilities. Could these detailed measurements eventually reveal subtle and unexpected deviations from our standard cosmological model, pointing astronomers toward new and unknown forms of dark energy or previously undetected forms of cosmic spatial curvature? From a more speculative viewpoint, the mind-boggling energies that are involved near these quasars ignite the imagination about the possibility of other, as yet unknown, astrophysical phenomena. Could their immense gravitational fields be capable of twisting space-time sufficiently to form transient wormholes or other exotic gravitational lensing patterns. Could these luminous and violent giants be hosting unimaginable and truly alien astrophysical entities, such as exotic compact objects like boson stars? Or could they be interacting with hypothetical cosmic strings that are passing nearby, leaving behind discernible and unique signatures for our most careful observers to find? Ultimately, these hyperluminous quasars symbolize humanity's relentless and unending quest to understand the cosmos at its most extreme and most fundamental levels. As astronomers and physicists continue to refine their instruments and their theoretical techniques, these powerful celestial beacons promise to deliver new discoveries that will not only enhance our astrophysical understanding, but will also have the potential to completely reshape our most fundamental conceptions of reality itself. Each new observation of these distant and brilliant objects thus becomes a thrilling and important step toward decoding the deepest cosmic mysteries that have captivated and inspired thinkers since the dawn of human consciousness. Beyond their immense scientific importance, these extraordinarily luminous and distant quasars also serve as profound and humbling reminders of nature's incredible capacity to surpass the limits of human imagination. They challenge scientists to venture beyond the safety and comfort of their established theoretical frameworks, urging them to explore new, radical, and often counterintuitive hypotheses, such as the effects of quantum gravity on the nature of singularities, alternative formulations of the geometry of space-time, or the existence of unconventional properties of dark matter. Could the spectacular luminosity and the incredibly rapid growth of these supermassive black holes be a sign of their interaction with previously undetectable quantum fields, or with hidden extra dimensions of reality that are currently beyond the reach of our perception? Astrophysicists also speculate on the observational signatures that may arise from the mergers of these quasars, rare and incredibly violent events that are expected to shake the very fabric of space-time itself. Such titanic and cataclysmic encounters, which would involve the collision and the eventual unification of 2 billion solar mass black holes, could emit powerful and detectable gravitational waves that could be observed by the next generation of space-based detectors. Could the detailed electromagnetic observations of these events, when correlated with their gravitational wave signatures, revolutionize our understanding of the nature of gravity, either confirming or refuting the predictions of Einstein's theory in the most extreme environments? Furthermore, theoretical physicists are exploring how these hyperluminous quasars might be able to illuminate deeper insights into the nature of entropy and the flow of information within the cosmos. The intense and complex energy transformations that are occurring near the event horizons of these objects provide us with unprecedented natural laboratories for testing some of the most profound and difficult concepts in modern physics, including the principles of black hole thermodynamics, the ideas of holographic information encoding, and even the subtle interactions that are thought to exist between gravity and the theory of quantum information. Could a detailed and long-term study of these quasars eventually lead to a resolution of the famous black hole information paradox, which remains one of the greatest and most stubborn unsolved mysteries in all of physics? From a cosmological perspective, the brightest of these quasars also serve as powerful probes of the fundamental assumptions of universal homogeneity and isotropy, which are the central pillars that underpin our entire standard model of cosmology. The detection of even slight and subtle irregularities or directional anomalies in the distribution of these quasars across the vast scales of cosmic distance could hint at the existence of large-scale cosmic anisotropies or significant deviations from our standard cosmological assumptions. This could potentially lead to paradigm-shifting revisions of our entire cosmological theory. In addition, the remarkable stability and the enduring visibility of these hyperluminous quasars over billions of years of cosmic time pose some intriguing possibilities for observational astronomy. Their persistent brightness on these immense timescales allows astronomers to compare the properties of their ancient emitted radiation with modern observations, which could potentially allow us to identify subtle cosmic variations over time, such as a drift in the values of the fundamental constants, a change in the nature of the physical laws, or an evolution in the properties of dark energy. Could these quasars be the ultimate cosmic reference points, allowing us to track the evolving nature of the universe itself across immense and otherwise inaccessible stretches of time? Moreover, the complex interplay that exists between these hyperluminous quasars and their host galaxies is opening up tantalizing new possibilities for understanding the processes of galaxy formation and evolution. A deeper understanding of how these incredibly energetic objects are able to impact the star formation rates, the morphology, and the chemical composition of their host galaxies is deepening our knowledge of the co-evolutionary relationship that exists between galaxies and their central supermassive black holes. Could it be that quasars of such astonishing and brilliant power are fundamentally shaping the destinies of their host galaxies, regulating the grand cosmic cycles of birth, destruction, and renewal over the course of eons? Even more provocatively, some physicists have begun to consider whether the most luminous of these quasars could shed some observational light on the existence of exotic cosmological objects like primordial black holes, which are hypothetical remnants of the Big Bang itself. Could the tiny, ancient primordial black holes that may have been captured in orbit around or are being consumed by these colossal supermassive black holes be leaving behind detectable and unique imprints on the quasar's radiation or on its gravitational wave emissions, revealing profound new insights into the physical conditions that existed just fractions of a second after the birth of our universe? Ultimately, these luminous quasars represent a new and exciting cosmic frontier, the exploration of which may forever alter our scientific understanding and our philosophical perspective. Their extraordinary and often paradoxical properties are posing some of the most fundamental questions we can ask. What unknown physical laws are awaiting discovery within their turbulent and fiery hearts? Do entirely new and undiscovered forms of matter or energy operate in these extreme and violent environments? Could the detailed and long-term study of these cosmic giants provide humanity with profound new insights into the nature of our own existence and our true place within the vast and mysterious universe in pursuing these celestial enigmas? Astronomers and physicists are embarking on one of humanity's most thrilling and important intellectual adventures, pushing the boundaries of our knowledge, inspiring technological innovation, and transforming our understanding of the universe from the smallest quantum scales to the grandest cosmic expanse. Exploring the radiant depths of these powerful cosmic beacons might, in time, even help us to unravel the deep and enduring mysteries that surround the nature of cosmic acceleration and the enigmatic properties of dark energy. Their incredible luminosity and their profound clarity at immense cosmological distances offer us an unparalleled and powerful tool for precisely mapping the expansion history of the entire universe. By meticulously charting the subtle variations in their luminosity across the vast scales of the cosmos, astronomers might one day be able to detect the faint and hidden signals or anomalies that could point to the existence of undiscovered components that are influencing the evolution of the cosmos. Could the subtle and complex patterns that are hidden deep within the ancient radiation of these extraordinary and brilliant quasars hold the key to resolving our era's greatest and most profound cosmological enigmas? From a gravitational perspective, these superluminous quasars also present us with tantalizing and unique opportunities for investigating any potential deviations from Einstein's cherished theory of general relativity. Their incredibly intense gravitational fields and their highly relativistic environments create the ideal and natural testing grounds for measuring the subtle and difficult-to-detect effects that are predicted by various modified theories of gravity, including the so-called scalar tensor theories, or the more exotic higher-dimensional models. Could the precise and detailed observations of the emission lines or the relativistic jets that are produced near their central engines ultimately provide us with the first empirical evidence that could support these revolutionary new theories of gravity and the very nature of spacetime? Furthermore, the complex magnetic field structures and the extreme plasma behaviors that are observed in the regions surrounding these luminous giants are opening up new windows into the regimes of plasma physics that are completely unattainable in any of our terrestrial laboratories. The detailed observations of the coherent electromagnetic flares, the violent magnetic reconnection events, and the powerful particle acceleration that occurs near these cosmic dynamos are offering astrophysicists a chance to better understand the fundamental magneto-hydrodynamic processes that govern a wide range of phenomena. From the flares on our own sun to the acceleration of cosmic rays and the nature of pulsar wind nebulae. Could the detailed and long-term studies of these quasars fundamentally enhance our knowledge of the principles of plasma physics, guiding significant advancements across a wide range of multiple scientific disciplines? Equally intriguing is the possibility that these supermassive and hyperluminous quasars could indirectly inform our ongoing searches for extraterrestrial intelligence. While their intense and powerful radiation would certainly render any nearby regions completely hostile to the kind of life that we know, their immense visibility and their recognizable radiation signatures across billions of light-years of space may serve as a kind of universal marker or a cosmic beacon, a signpost that would be recognizable even by distant and technologically advanced civilizations. Could these remarkable and powerful phenomena play a role in any hypothetical strategies for interstellar communication? Or could they serve as natural and reliable reference points in any form of extraterrestrial navigation? The very existence of such objects forces us to consider the universe on a scale that is both humbling and inspiring, a universe of immense power, beauty, and mystery.
Imagine standing at the edge of an abyss, a place of such profound emptiness that it seems to contain nothing at all. No light, no sound, no matter, not even the familiar framework of space and time. This is the conceptual void from which our entire universe, in all its vastness and complexity, is thought to have been born. It is the ultimate mystery, the question that has haunted philosophers, poets, and scientists for millennia. Why is there something when there could have been nothing? As you gaze up at the star-dusted canvas of the night sky, you are not just looking at distant points of light, you are looking back in time, at the echoes of a cosmic story that began with a mystery so deep it challenges the very limits of human understanding. And yet, modern physics has begun to peel back the veil of this nothingness, and what it has found is not an empty, passive stage, but a vibrant, seething, and endlessly creative reality. The void is not a void. It is a quantum sea, a turbulent ocean of energy and potential, a place where the rules of our everyday classical world dissolve, and a stranger, more fundamental logic takes over. This is the realm of the quantum vacuum, a place where particles can be in many places at once, where they can be connected across vast, cosmic distances in an instant, and where the very act of observation seems to shape the nature of reality itself. This strange and beautiful vision of a potent, creative emptiness is not a new idea. It is a concept that has resonated through human history, an intuition that has found expression in some of our most ancient philosophical and spiritual traditions. The ancient Greeks spoke of chaos, the formless, primordial abyss that existed before the ordered cosmos. In the rich contemplative traditions of the East, we find even more striking parallels. The Hindu concept of shunyata, often translated as emptiness or voidness, is not a nihilistic concept of non-existence. It is the understanding that all phenomena are devoid of any fixed, independent self-nature, and that they arise from a common, underlying ground of being that is itself empty of any inherent characteristics, yet full of infinite potential. The Tao Te Ching, the foundational text of Taoism, begins with a meditation on the Wu, the unnameable, formless void that is, paradoxically, the mother of the 10,000 things, the entirety of the manifest world. It is a remarkable convergence of thought that these ancient, intuitive cosmologies, born from deep introspection, seem to be pointing towards the same fundamental truth that modern physics is now uncovering through the rigorous language of mathematics and experimentation. Quantum mechanics, that strange and wonderful pillar of modern science, has given us a new language to describe this creative void. It tells us that even in a perfect vacuum, a space cooled to absolute zero and shielded from all external influence, there is an incessant, irreducible quantum jiggle. This is the world of quantum fluctuations, a place where pairs of virtual particles and their antimatter counterparts are constantly bubbling into existence, borrowing a tiny amount of energy from the vacuum for an immeasurably short time before annihilating each other and returning their borrowed energy to the void. This is not a theoretical fantasy. It is a direct consequence of one of the most fundamental principles of nature, Werner Heisenberg's uncertainty principle. Formulated in 1927, this principle states that there is an irreducible trade-off in our knowledge of certain pairs of properties of a quantum system. The more precisely you know a particle's position, the less precisely you can know its momentum. This fundamental uncertainty means that no region of space can ever be truly, definitively empty. The very act of measuring a region to confirm its emptiness would, by the uncertainty principle, inject energy into it. At the most fundamental level, there is no such thing as a truly empty or static space. Every point in the cosmos is permeated by a web of quantum fields, one for each type of fundamental particle. These fields are never completely at rest. They are always vibrating, always fluctuating, even in their lowest energy state. This irreducible minimum energy of the vacuum is known as zero-point energy. It is the baseline hum of the universe, the silent, ever-present music of the void. And this is not just a mathematical abstraction. The physical effects of these virtual particles and their zero-point energy can be measured. The Casimir effect, predicted by the Dutch physicist Hendrik Casimir in 1948 and later confirmed experimentally, shows that two uncharged parallel metal plates placed very close together in a vacuum will be pushed together by an invisible force. This force is not gravity, nor electromagnetism. It is the pressure of the quantum vacuum itself. The space between the plates can only accommodate virtual particles of certain wavelengths, while the space outside the plates can accommodate all wavelengths. This creates a pressure differential, a net force pushing the plates together. The void itself can exert a physical force. It is a stunning, tangible demonstration that what we call emptiness is, in fact, a dynamic, energetic, and powerful medium. The creative potential of this quantum vacuum is not limited to the fleeting dance of virtual particles. It may be the very source of our entire universe. The theory of cosmic inflation, one of the cornerstones of modern cosmology, proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated, exponential expansion. The driving force behind this inflation is thought to have been the energy of a quantum field, known as the inflaton field, trapped in a high-energy, the false vacuum state. As this field relaxed to its true lower energy state, it released its stored energy, flooding the nascent universe with the matter and radiation we see today. In this picture, the universe is a kind of macroscopic quantum fluctuation, a bubble of reality that was inflated to cosmic proportions by the energy of the void. This idea leads to an even more mind-boggling possibility, the quantum foam. First envisioned by the physicist John Wheeler, This is the idea that at the smallest possible scales of distance, the so-called Planck length, an unimaginably small 10 to the power of minus 35 meters, the very fabric of space-time is not smooth and continuous, but a chaotic, turbulent foam of microscopic black holes and wormholes, constantly being created and annihilated by quantum fluctuations. At this fundamental level, our familiar notions of space and time break down. This is the realm of quantum gravity, the yet-to-be-discovered theory that will unify Einstein's general relativity with quantum mechanics. In this foamy quantum reality, a sufficiently large fluctuation could, in principle, give rise to a new, expanding universe. Our cosmos could be a single, fortunate bubble that emerged from this infinite, eternal sea of quantum potential. This is the scientific version of a universe from nothing, a concept explored by physicist Lawrence Krauss. The nothing in this context is not an absolute philosophical void, but the rich, dynamic, and endlessly creative quantum vacuum. This completely inverts our classical understanding of reality. We no longer see the void as a passive, empty stage upon which the cosmic drama unfolds. We see the void itself as the primary actor, the generative source, the mother of all that is. The emptiness between the stars is not an absence. It is the presence of an infinite potential, a potential that, some 13.8 billion years ago, blossomed into the vast, complex, and beautiful universe we call home. And so, as you lie in the quiet of the night, as your consciousness begins to drift into the silent, inner space of sleep, you are, in a sense, returning to this primordial state. You are entering your own personal quantum vacuum, a space of pure potential, a space where new thoughts, new dreams, and new realities can be born from the creative silence of your own being. In the early 1980s, the standard Big Bang model, while remarkably successful in describing the evolution of the universe from a hot, dense state, was facing a series of deep, conceptual puzzles. It was like having a perfectly working car, but with no idea how the engine was built or why it had started in the first place. Then, on a cold December night in 1979, a young American physicist named Alan Guth, poring over his equations, had what he later called spectacular realization. He had stumbled upon the cosmic ignition key. The theory he conceived that night, the theory of cosmic inflation, would not just solve the lingering puzzles of the Big Bang, it would fundamentally reshape our understanding of the first, infinitesimal moments of creation, and it would do so by unleashing the immense, creative power of the quantum vacuum. The story that inflation tells is one of almost unimaginable drama. It proposes that in the very first flicker of time, between roughly 10 to the power of minus 36 and 10 to the power of minus 32 seconds after the Big Bang, the universe underwent a period of astonishing, hyper-accelerated, exponential expansion. It was a cosmic growth spurt of truly epic proportions. During this fleeting, almost timeless instant, the size of the universe increased by a factor of at least 10 to the power of 26, a number so large it is difficult to represent with analogies. It is like taking an object smaller than a single proton and stretching it to the size of a grapefruit in a time far shorter than it takes light to cross that same proton. This is not just an expansion in space, it is an expansion of space itself, a stretching of the very fabric of reality at a rate that completely dwarfs the speed of light. The engine that powered this explosive growth, according to inflationary theory, was the energy of a quantum field, dubbed the inflaton field, which was momentarily trapped in a high-energy, unstable state known as a false vacuum. Imagine a ball perched precariously in a small divot at the very peak of a vast, steep hill. It possesses a huge amount of potential energy, and it is in a state of metastable equilibrium. A tiny quantum jiggle is all it would take to send it cascading down the hill, releasing its stored potential energy as the kinetic energy of motion. The false vacuum of the early universe was like this ball at the top of the hill. It was a state of incredibly high and uniform energy density, and this energy had a peculiar and powerful property. It exerted a strong negative pressure. which, according to Einstein's theory of general relativity, creates a powerful gravitational repulsion. It was this anti-gravity of the false vacuum that drove the exponential inflationary expansion. Eventually, this false vacuum state decayed, like the ball rolling down the hill, into the true lower energy vacuum state of our current universe. This process, called reheating, was a cataclysmic event. The immense energy that had been stored in the inflaton field was released, flooding the now vast, empty universe with a hot, dense, and uniform soup of fundamental particles and radiation. This is the starting point of the standard, hot Big Bang model. Inflation, in this sense, is not an alternative to the Big Bang. It is a prequel, a brilliant and necessary prologue that sets the stage and explains the seemingly miraculous initial conditions from which the rest of cosmic history unfolded. The true elegance of inflationary theory lies not just in its dramatic narrative, but in its remarkable ability to solve the deep, conceptual puzzles that had plagued the standard Big Bang model. One of the most profound of these was the horizon problem. When we observe the cosmic microwave background CMB, the faint, relic radiation from the infant universe, we find that it has an almost perfectly uniform temperature in all directions, to an accuracy of about 1 part in 100,000. This is a profound mystery. In the standard Big Bang model without inflation, regions of the sky that are on opposite horizons today were never in causal contact with each other. They were too far apart for light, or any other signal, to have traveled between them in the time since the beginning of the universe. So, how could they have possibly reached the same temperature? It is as if you walked into a vast, cavernous room and found that the temperature at every single point was identical to within a tiny fraction of a degree, without any heating or cooling system to have ever been turned on. Inflation provides a beautifully simple solution. Before the period of exponential expansion, the region of space that would eventually become our entire observable universe was an incredibly tiny, subatomic patch. It was so small that it was in perfect causal contact with itself. There was plenty of time for all parts of this patch to interact, to exchange energy, and to reach a state of thermal equilibrium, a state of uniform temperature. Inflation then took this tiny, smooth, and causally connected region and stretched it to astronomical proportions in the blink of an eye. The uniformity was preserved, locked into the expanding fabric of space, creating the smooth, isotropic universe we see today. The second major puzzle solved by inflation is the flatness problem. General relativity tells us that the geometry of spacetime is determined by its total density of matter and energy. If this density is above a certain critical value, the universe will be closed, like the surface of a sphere, and will eventually collapse. If it is below the critical value, the universe will be open, like the surface of a saddle, and will expand forever. The flat universe of Euclidean geometry is a special knife-edge case, corresponding to a density that is exactly equal to the critical density. Our observations tell us that our universe is astonishingly, exquisitely flat. For this to be the case, the initial density of the universe at the time of the Big Bang would have had to be fine-tuned to a degree of precision that is almost beyond comprehension, about 1 part in 10 to the power of 60. This seems like an absurdly improbable coincidence. Inflation solves this problem in a natural and elegant way. Any initial curvature that the universe may have had, whether positive or negative, would have been stretched out and flattened by the immense exponential expansion. In the same way that inflating a small, wrinkled balloon to the size of the Earth would make its surface appear perfectly flat to an observer on it. Inflation drives the geometry of the universe so close to perfect flatness that it is, for all practical purposes, indistinguishable from it. But inflation does more than just solve old problems. It makes a remarkable and testable prediction. The theory states that the tiny, unavoidable quantum fluctuations as in the inflaton field itself during the period of inflation would not have been smoothed out. Instead, they would have been stretched to macroscopic and even astronomical scales. These stretched-in-time quantum fluctuations would have become the seeds of cosmic structure, the tiny variations in density that, over billions of years and would grow under the influence of gravity to become all the galaxies, the clusters of galaxies, and the vast cosmic web that we see today. The specific statistical properties of these primordial fluctuations, they're near, but not perfect. Scale invariants are a unique fingerprint of inflation, and they have been confirmed with stunning precision by our detailed maps of the cosmic microwave background. We are, in the most literal and profound sense, the children of quantum fluctuations. Our entire cosmic home, with all its grandeur and complexity, is a macroscopic fossil of the inherent uncertainty of the primordial quantum void, a void that was momentarily supercharged with an incredible inflationary energy. The theory of inflation, in its more modern and sophisticated forms, has led to a concept that is even more profound and mind-altering than the Big Bang itself: the idea of eternal inflation and the multiverse. The Russian-American cosmologist Andrei Linde, one of the key architects of modern inflationary theory, realized that the process of inflation, once started, may be very difficult to stop. In his model of chaotic inflation, the inflaton field is not a single uniform entity, but a field that has different random values in different regions of the primordial universe. In some regions, the field will quickly roll down its potential hill. Inflation will end, and a bubble universe like ours will be born in a hot Big Bang. But in other regions, quantum fluctuations can kick the field up the hill, causing inflation to continue, and even to become a self-reproducing eternal process. In this scenario, the end of inflation in our region was just a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate and constantly spawning new bubble universes. The Big Bang was not a singular, unique event in the history of time. It is a common, ongoing process in the vast, eternal landscape of the multiverse. This is a vision of reality that is almost impossible to fully comprehend. Our entire observable universe, with its hundreds of billions of galaxies, is just one bubble in an infinite, bubbling foam of other universes. And these other universes may not be like our own. The decay of the inflaton field in each bubble could lead to different vacuum states, resulting in different fundamental particles, different forces of nature, different physical laws. There could be universes with 2 dimensions of space, or 10. Universes where gravity is a repulsive force, or where the speed of light is different. Most of these universes would be sterile, bizarre, and inhospitable wastelands, incapable of supporting any form of complexity or life. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle to be explained. It becomes a simple selection effect. We find ourselves in a universe that is hospitable to life, for the same reason that we find ourselves living on a planet with liquid water and a breathable atmosphere. We could not exist to ask the question in any of the other, far more numerous, inhospitable environments. The multiverse, in this sense, provides a scientific, albeit untestable, explanation for the anthropic principle. The idea of eternal inflation and the multiverse is on the cutting edge of theoretical physics, and it is by no means universally accepted. Critics point out that it is, by its very nature, unobservable, and therefore may not be a truly scientific theory. But its proponents argue that it is a natural and almost unavoidable consequence of combining our best theories of cosmology and quantum field theory. And there may be ways to search for indirect circumstantial evidence. If our bubble universe had, in its distant past, collided with another bubble, it might have left a bruise on our cosmos, a specific circular pattern of temperature fluctuations in the cosmic microwave background. The search for such a cosmic scar is an active, if long-shot, area of research. Whether the multiverse is a physical reality or a beautiful mathematical dream, the theory of inflation has fundamentally and irrevocably changed our view of our own origins. It has taken the Big Bang from a mysterious, unexplained singularity and placed it within a larger, dynamic, and potentially eternal cosmic context. It has shown us how the grand, macroscopic structure of our universe can be born from the subtle, microscopic quantum fluctuations of the void. And it has opened our minds to the breathtaking possibility that our entire cosmos is just a single, fleeting note in an infinite and eternal cosmic symphony. The concept of the Big Bang itself, the central event in our cosmic story, is one that is often shrouded in misconception. The popular image is that of a gigantic firework, a singular explosion happening at a specific point in a pre-existing empty space. But this picture is fundamentally wrong. The Big Bang was not an explosion in space. It was an explosion of space. It was not an event that happened at a particular location. It was an event that happened everywhere at once. To grasp this counterintuitive idea, the analogy of an expanding balloon is helpful. If you imagine our three-dimensional space as the two-dimensional surface of a balloon, and you draw a number of dots on this surface to represent galaxies, then as you inflate the balloon, you will see that every dot is moving away from every other dot. An observer on any given dot would see all the other dots receding from them, and the further away a dot is, the faster it would appear to be moving away. There is no center to this expansion on the surface of the balloon. The expansion is happening everywhere. The fabric of the balloon itself is stretching. In the same way, the expansion of the universe is a stretching of the fabric of space-time. Every point in our current universe, including the point where you are right now, was part of that initial, infinitely hot and dense state. The Big Bang happened right here and everywhere else. This is a direct consequence of Einstein's general theory of relativity, which describes space and time not as a static, absolute background, but as a dynamic, physical entity that can be bent, warped, and stretched by the presence of matter and energy. The Big Bang, then, is not a theory of the origin of the universe from nothing. It is a theory of the evolution of the universe from a very hot, dense, and rapidly expanding initial state. It does not, in its standard form, address the question of what caused the Big Bang, or what, if anything, came before it. Those are questions that lie beyond the domain of the theory, in the realm of quantum gravity and the speculative cosmologies we have discussed. The story that the Big Bang does tell is the story of the first 14 billion years of our universe's life, a story of cooling, of expansion, and of the gradual emergence of complexity from a state of primordial simplicity. In the first fractions of a second, the universe was an unimaginably hot and dense soup of fundamental particles, quarks, leptons, and the force-carrying bosons, a state known as a quark-gluon plasma. As the universe expanded and cooled, this plasma froze out. After about 1 microsecond, the quarks bound together to form the protons and neutrons that make up the nuclei of atoms. For the next few minutes, in a process known as Big Bang nucleosynthesis, these protons and neutrons fuse together to form the nuclei of the lightest elements, mostly hydrogen and helium, with trace amounts of lithium. The universe was still a hot, dense, and opaque plasma. The temperature was so high that electrons were not bound to the atomic nuclei. This sea of free electrons acted like a dense fog, constantly scattering photons of light, preventing them from traveling any significant distance. The universe was dark, not because there was no light, but because the light was trapped. This period lasted for about 380,000 years. Then, as the universe continued to expand and cool, it reached a critical temperature of about 3,000 Kelvin. At this point, the electrons had slowed down enough to be captured by the atomic nuclei, forming the first stable, neutral atoms. This event is known as recombination. Suddenly, the fog lifted. The universe became transparent to light. The photons that were present at that time were now free to travel unimpeded through space, and they have been traveling ever since. Their wavelengths stretched by the subsequent expansion of the universe from high-energy visible light into the cool, faint microwaves that we detect today. This is the cosmic microwave background, the oldest light in the universe, a beautiful, uniform glow that comes to us from all directions in the sky. It is a baby picture of our universe, a snapshot of the moment it first became transparent, a fossil that carries with it a wealth of information about the conditions of the early cosmos. The story of the Big Bang is a story of transformation, a story of how, from a state of almost perfect uniformity and simplicity, all the rich and complex structures we see today, the stars, the galaxies, the planets, and ourselves, were gradually born. It is a story that is written in the light of the distant stars, in the composition of the elements, and in the faint, ancient glow of the cosmic microwave background. It is our story. As our journey through the cosmos brings us closer to the present day, we encounter the universe's most profound and perplexing mystery, the existence of dark energy. This is not a subtle theoretical curiosity. It is the dominant component of our universe, making up roughly 68% of its total energy density. It is the invisible, silent force that is shaping the ultimate destiny of our cosmos, and we have almost no idea what it is. The discovery of dark energy in 1998 was a complete surprise. Two independent teams of astronomers, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, were using Type Ia supernovae as standard candles to measure the expansion rate of the universe at different times in its history. A Type Ia supernova is the thermonuclear explosion of a white dwarf star, and it always has the same intrinsic brightness, making it a perfect cosmic yardstick. The teams expected to find that the expansion of the universe was slowing down, as the mutual gravitational attraction of all the matter in the cosmos should be acting as a brake. To their astonishment, they found the exact opposite. The distant supernovae were dimmer than expected, which meant they were further away than they should have been if the expansion was slowing down. The expansion of the universe is accelerating. This groundbreaking discovery, which earned its leaders the 2011 Nobel Prize in Physics, implied the existence of a new, previously unknown form of energy with a strange and powerful property, a strong negative pressure that acts as a form of cosmic anti-gravity, pushing space-time apart. This is what we call dark energy. The simplest and most natural candidate for dark energy is the energy of the quantum vacuum itself, the zero-point energy we discussed earlier. In the context of Einstein's general relativity, a constant vacuum energy density would manifest as a cosmological constant, a term that Einstein himself had introduced into his equations in 1917, only to later retract it as his biggest blunder when Edwin Hubble discovered the universe was expanding. In a beautiful historical irony, modern cosmology has resurrected Einstein's blunder and made it the centerpiece of our standard cosmological model. A universe dominated by a cosmological constant has a strange and counterintuitive property. As space expands, the density of matter and radiation decreases, as they are spread out over a larger volume, but the density of vacuum energy remains constant. This means that as the universe gets bigger, the total amount of dark energy increases. It is as if new energy is being created from the expanding space itself. In the early universe, when the density of matter and radiation was very high, the effects of dark energy were negligible. But as the universe expanded and thinned out, dark energy gradually became the dominant component. It took over from gravity as the primary driver of cosmic evolution about 5 billion years ago, and it has been accelerating the expansion ever since. The problem, as we have seen, is the vacuum catastrophe. The theoretical value of the vacuum energy calculated from quantum field theory is an absurd 120 orders of magnitude larger than the observed value of dark energy. This colossal discrepancy has led many physicists to believe that the simple identification of dark energy with vacuum energy must be wrong. This has led to a host of alternative theories. Perhaps dark energy is not a constant, but is a dynamic entity, a new quantum field dubbed quintessence that is slowly rolling towards its minimum energy state. In this scenario, the rate of cosmic acceleration could change over time, leading to a different ultimate fate for the universe. Or perhaps our understanding of gravity is wrong. Maybe general relativity needs to be modified on cosmological scales. These modified gravity theories attempt to explain the accelerated expansion without invoking any new form of energy. They propose that gravity itself becomes repulsive on very large distances. Distinguishing between these different possibilities is one of the primary goals of modern cosmology. Observatories like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the distribution of galaxies and the history of cosmic expansion with unprecedented precision, which will allow us to measure the properties of dark energy and to test whether it has changed over time. The nature of dark energy is not just a question for physicists. It is a question that touches on the ultimate fate of our universe. A universe dominated by a constant dark energy is destined for a big freeze. A universe dominated by a phantom energy that grows stronger over time is destined for a big rip. And a universe where dark energy could one day decay or change its sign could be destined for a big crunch. We live in a universe whose destiny is being written by an invisible, mysterious, and powerful force. A force whose true nature remains one of the greatest and most profound challenges in all of science. The empty space that surrounds us is not empty at all. It is a dynamic, energetic, and powerful entity. A cosmic protagonist whose story we are only just beginning to understand. The idea that our universe might not be the only one, that it could be part of a vast, perhaps infinite, multiverse, is a concept that has migrated from the realms of science fiction and philosophy into the heart of modern theoretical physics. It is a breathtaking and humbling idea, one that, if true, would represent the final and most profound step in the Copernican revolution. The long historical process of decentering humanity from a privileged position in the cosmos. The concept of the multiverse is not a single, coherent theory, but rather a consequence of several of our most ambitious and successful physical theories. We have already encountered one of its most compelling sources, the theory of eternal cosmic inflation. In this picture, our universe is just one bubble that formed when a small patch of an eternally inflating meta-universe decayed into a lower energy state. Other bubbles are constantly forming, each potentially with different physical laws, constants, and even different numbers of dimensions. This creates a vast, level 2 multiverse of disconnected, parallel realities. Another powerful argument for the multiverse comes from the many worlds interpretation of quantum mechanics. As we discussed, this interpretation, first proposed by Hugh Everett, solves the measurement problem by positing that the wave function never collapses. Instead, every quantum measurement causes the universe to split into multiple branches, with each branch corresponding to one of the possible outcomes. This creates a level 3 multiverse, a constantly branching tree of parallel realities. In this multiverse, there are an infinite number of yous, each living out the consequences of a different quantum outcome. There is a version of you who is reading this, and a version of you who decided to go for a walk instead. Every possibility is realized somewhere in this vast quantum multiverse. A third and more straightforward type of multiverse is the level 1 multiverse. This is simply the idea that our observable universe, the region of space from which light has had time to reach us since the Big Bang, is just a small patch of a much larger and possibly infinite universe. If space is infinite, then in that infinite volume, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far beyond our cosmic horizon, there is another galaxy, another solar system, another Earth, and another you, an identical copy living out an identical life. And there are an infinite number of such copies. This is a staggering and deeply unsettling thought, one that challenges our sense of individuality and uniqueness. Finally, there is the most abstract and philosophical type of multiverse, the level 4, or mathematical universe, proposed by physicist Max Tegmark. This is the idea that physical reality is, at its core, a mathematical structure. And since all consistent mathematical structures exist in a timeless, Platonic sense, then all possible mathematical structures exist as physical realities. Our universe is just one, particularly complex, mathematical structure, one that happens to have the right properties to allow for the emergence of self-aware substructures, like us, who can contemplate the mathematical nature of their own existence. The multiverse, in all its forms, provides a powerful, if controversial, framework for addressing the fine-tuning problem. The fact that the physical constants of our universe seem to be so exquisitely tuned to allow for the existence of life is no longer a miracle that requires a supernatural explanation. It is a simple selection effect. We find ourselves in a universe that is hospitable to life because it is the only kind of universe we could find ourselves in. We are the survivors of a cosmic lottery of unimaginable proportions. The primary criticism of all multiverse theories is that they are, by their very nature, untestable. We can never travel to another bubble universe or communicate with a parallel branch of the quantum wave function. This has led some to argue that the multiverse is not a scientific theory, but a metaphysical one. But its proponents argue that the theories from which the multiverse arises, like inflation and quantum mechanics, are themselves highly testable. If these theories continue to pass every experimental test we throw at them, then we may be forced to take their more bizarre consequences, like the multiverse, seriously, and there may be indirect, circumstantial ways to search for evidence. The cosmic bruise from a collision with another bubble universe is one such possibility. The search for a variation in the fundamental constants of nature across the sky is another. Whether the multiverse is a physical reality or not, the very fact that it is a serious topic of discussion among many of the world's leading physicists is a testament to how far our cosmic horizons have expanded. It is a concept that forces us to confront the true scale of reality, to question our most basic assumptions about our own uniqueness, and to embrace a vision of the cosmos that is infinitely richer, stranger, and more magnificent than we ever dared to imagine. As we gaze out into the cosmos, our vision is fundamentally limited. The night sky appears as a vast dark dome, but this is an illusion. We are not looking out at a static three-dimensional space. We are looking back in time. The light from the moon takes a little over a second to reach us, so we see it as it was a second ago. The light from the sun takes 8 minutes. The light from our nearest stellar neighbor, Proxima Centauri, takes over 4 years. And the light from the Andromeda Galaxy, our closest major galactic neighbor, has been traveling for 2.5 million years. When we look at the most distant galaxies visible in the James Webb Space Telescope, we are seeing them as they were over 13 billion years ago. When the universe was just a toddler, this intimate connection between distance and time defines our cosmic horizon. Because the universe has a finite age of approximately 13.8 billion years, and because light travels at a finite speed, there is a fundamental limit to how far we can see. The boundary of our observable universe is not a physical wall, but a temporal one. It is the distance from which light has had just enough time to reach us since the Big Bang. We can never, even in principle, see what lies beyond this horizon. The universe may be infinite, but our view of it is finite. The situation is made even more profound by the accelerating expansion of the universe. Not only is there a horizon that limits our view of the past, but there is also an event horizon that limits our view of the future, because space itself is expanding, and this expansion is accelerating. Distant galaxies are receding from us at ever-increasing speeds. There is a critical distance beyond which galaxies are receding from us faster than the speed of light. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this event horizon will never be able to reach us. They will be causally disconnected from our future. They will, in a sense, disappear from our universe. The night sky of the far future will be a profoundly lonely place. As more and more galaxies recede beyond our event horizon, the cosmic landscape will become increasingly empty. Eventually, only the members of our own gravitationally bound local group of galaxies will remain visible. A future civilization, looking up at the sky, might conclude that they live in a single island universe, forever unaware of the vast cosmic ocean that we are privileged to still be able to see. This concept of an event horizon, a one-way membrane that separates the observable from the unobservable, is most famously associated with black holes. A black hole is a region of space-time where gravity is so intense that nothing, not even light, can escape. Its event horizon is the point of no return. Any object or any information that crosses this boundary is seemingly lost to the outside universe forever. In the 1970s, Stephen Hawking revolutionized our understanding of black holes by showing that they are not completely black. Due to quantum effects at the event horizon, the constant creation and annihilation of virtual particle pairs from the quantum vacuum black holes should slowly emit a faint thermal radiation. This Hawking radiation causes the black hole to lose mass and, over immense timescales, to eventually evaporate completely. This brilliant discovery, which elegantly weaves together the principles of general relativity, quantum mechanics, and thermodynamics, also gave rise to one of the deepest paradoxes in modern physics, the black hole information paradox. According to the fundamental principles of quantum mechanics, information can never be destroyed. The total amount of information in a closed system must always be conserved. But if you throw an encyclopedia, with all its rich and complex information, into a black hole, that information seems to be lost forever behind the event horizon. And when the black hole evaporates, the Hawking radiation it emits appears to be purely thermal and random, containing no memory of the information that fell in. So, where did the information go? Is it truly destroyed, in violation of one of the most sacred principles of physics, or does it somehow escape, subtly encoded in the quantum correlations of the outgoing radiation? This paradox has been a major driver of research in theoretical physics for decades, and its resolution is thought to be a key step towards a full theory of quantum gravity. Recent theoretical work has suggested that the information is not lost, but is preserved on the event horizon itself, a concept related to the holographic principle, which posits that all the information in a three-dimensional volume of space can be encoded on its two-dimensional boundary. The existence of horizons, both cosmological and black hole, is a profound and humbling feature of our universe. It tells us that there are fundamental, built-in limits to our knowledge. There are parts of the cosmos and aspects of nature that may forever lie beyond the reach of our direct observation. But they are also a powerful spur to our theoretical imagination, forcing us to devise new and creative ways to understand the realities that are hidden from our view. They are a reminder that the universe is not a transparent, open book, but a deep and multi-layered mystery. A mystery whose most profound secrets are often hidden right at the very edge of what we can see. The grand narrative of our cosmos, as told by the standard Big Bang model, is a linear one. It is a story with a definite beginning, a long period of evolution, and a potential final end. But is this the only possible story? Could the universe be a more timeless, more cyclical entity, an eternal dance of creation and destruction, with no absolute beginning or end? This idea of a cyclic universe is one of the oldest and most enduring in human thought. It is found in the concept of the kalpas in Hindu cosmology, vast time cycles of cosmic creation, maintenance, and dissolution. It is present in the philosophy of the ancient Stoics, with their idea of a great year, at the end of which the universe is consumed by fire and then reborn. And it is a concept that has been given a new, scientific life in some of the most advanced and speculative theories of modern cosmology. One of the most well-developed of these is the ekpyrotic or cyclic model, proposed by physicists Paul Steinhardt and Neil Turok. This model is rooted in the ideas of string theory and extra dimensions. It envisions our universe as a three-dimensional brane, or membrane, floating in a higher dimensional space, or bulk. There is another, parallel brane nearby. In this picture, the Big Bang is not the beginning of time, but is the result of a gentle, periodic collision between our brane and this other brane. Each collision releases a tremendous amount of energy, which is converted into the hot, dense matter and radiation of a new cosmic cycle. After the collision, the branes bounce apart, and our universe expands and cools, allowing for the formation of galaxies, stars, and planets. But this expansion is not destined to continue forever. A form of dark energy. In this model, a potential energy between the branes eventually causes the expansion to slow down and the branes to begin to move back towards each other, drawn together by a spring-like force. This leads, after a period of slow contraction, to another gentle collision, another Big Bang, and the beginning of a new cycle. Each of these cycles could last for 1 trillion years or more, an almost unimaginable timescale from a human perspective, but just a single beat in the eternal rhythm of the cosmos. This cyclic model has several attractive features. It elegantly solves the horizon and flatness problems of the standard Big Bang model without the need for a period of cosmic inflation. The smoothness of our universe is a result of the long period of slow contraction before the last bang, which had plenty of time to smooth out any irregularities. It also provides a natural explanation for dark energy as the force that drives the cycles. And most profoundly, it eliminates the need for an initial singularity, the point of infinite density and temperature where the laws of physics break down. In a cyclic universe, there is no absolute beginning. The universe has always existed and will always exist in an endless sequence of cosmic epochs. However, the cyclic model is not without its challenges. The physics of the brane collision, the bounce from a contracting phase to an expanding one, is incredibly complex and requires a full and as yet unknown theory of quantum gravity to be described accurately. And the model must also contend with the second law of thermodynamics. If entropy or disorder increases with each cycle, how can the universe return to the same low entropy state at the beginning of each new cycle? The proponents of the model argue that the vast expansion that occurs during each cycle so dilutes the entropy that it becomes negligible, effectively resetting the cosmic clock. Another related idea is the conformal cyclic cosmology (CCC) proposed by the eminent physicist Roger Penrose. In this model, the universe does not bounce, but expands forever. However, Penrose argues that in the very far future of our universe, after all the black holes have evaporated and only a cold, thin gas of photons and other massless particles remains, the universe loses its sense of scale. In this state, the infinitely large and cold future of our eon becomes mathematically equivalent, via a conformal transformation, to the hot, dense, low entropy state of a Big Bang for a new eon. The end of one universe becomes the beginning of the next. The cyclic models, in all their forms, offer a radically different vision of our cosmic story. They replace the linear, one-off narrative of the standard Big Bang with a more timeless, more eternal, and perhaps more philosophically satisfying picture of a universe that is constantly renewing and reinventing itself. While still a minority view among cosmologists, the idea of a cyclic universe is a powerful reminder that our current understanding is still provisional, and that the ultimate truth about our cosmic origins may be far stranger and far more beautiful than we can yet imagine. The apparent, exquisite fine-tuning of the fundamental constants of nature to allow for the existence of life is one of the most profound and philosophically charged mysteries in all of science. It is a puzzle that seems to hint at something deeper, something beyond the standard, materialistic worldview. Why is the strength of gravity just right to allow for long-lived stars? Why is the mass of the neutron just slightly heavier than the mass of the proton? A delicate balance that allows for the stability of atomic nuclei. Why is the cosmological constant so incredibly, exquisitely small, allowing for the formation of galaxies? This fine-tuning problem has led to the formulation of the anthropic principle, a controversial but powerful idea that attempts to explain this cosmic coincidence by invoking our own existence as observers. The weak anthropic principle is a relatively straightforward and almost tautological statement. It simply says that the conditions we observe in the universe must be compatible with the existence of observers. It is a form of selection bias. We find ourselves in a universe that is suitable for life because we could not have found ourselves in one that wasn't. It is a valid, but not particularly explanatory, principle. The strong anthropic principle, however, makes a much bolder and more metaphysical claim. It suggests that the universe is, in some sense, compelled to have properties that allow for the emergence of life and consciousness. This can be interpreted in several ways, from the theological, a divine designer, to the teleological, a cosmic purpose. The anthropic principle, in its weak form, finds a natural and scientific home in the context of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of other universes, each with its own randomly assigned set of physical constants. Then the fine-tuning problem dissolves. It is no longer a miracle that we find ourselves in a life-friendly universe. It is a statistical inevitability. We are simply living in one of the rare, habitable oases in a vast, sterile cosmic desert. This is a powerful and elegant explanation, but it relies on the existence of unobservable parallel realities. But is there a way to have a single, self-consistent universe without resorting to either a multiverse or a divine designer? This is the idea behind the bootstrap picture of the universe, a concept that has been a recurring dream in theoretical physics. The bootstrap hypothesis, in its most ambitious form, suggests that the universe is a completely self-consistent and unique whole. There is only one possible way for the universe to be: the values of the fundamental constants, the properties of the particles, the laws of physics themselves, are not accidental or random. They are all fixed by the requirement of overall mathematical and logical consistency. The universe, in a sense, pulls itself up by its own bootstraps. It is the way it is because it is the only way it could be. This is a vision of a universe that is not just described by mathematics, but is governed by a deep, underlying logical necessity. In this picture, there is no need for an anthropic principle to explain fine-tuning, because there is nothing to fine-tune. The constants have the values they do for the same reason that the ratio of a circle's circumference to its diameter is pi. It is a mathematical truth. The bootstrap dream was particularly popular in the 1960s in the context of the strong nuclear force, but it fell out of favor with the rise of the Standard Model, which seemed to have a number of arbitrary free parameters. However, the dream has not entirely died. The quest for a final, unified theory of everything, like string theory, is, in a sense, a quest for a bootstrap explanation. The hope is that a final theory will have no free parameters, that it will uniquely determine all the properties of our universe from a single, elegant set of principles. In the absence of such a final theory, the anthropic principle can be seen as a kind of poor man's bootstrap. It is a way of relating the properties of the universe to our own existence, a partial and existential form of self-consistency. When we observe a wild flower, we are also observing the universe that gave rise to it. A universe with the right chemistry, the right stellar evolution, the right physical laws. The organism and its universe are a self-consistent whole. The hope is that one day, our understanding will be so complete that when we observe a single electron, we will be able to deduce the properties of the entire universe from the requirement of self-consistency. We will find, as the poet William Blake wrote, a world in a grain of sand and a heaven in a wild flower. And the debate between the anthropic multiverse picture and the bootstrap unique universe picture is a debate about the very nature of physical law. Are the laws of nature contingent, accidental, and just one of a vast number of possibilities, or are they necessary, unique, and fixed by a deep, underlying logic? It is a debate about chance versus necessity at the most fundamental level of reality, and it is a debate that is far from being resolved. The quest to understand the universe inevitably leads us back to a profound and perplexing riddle, a riddle that lies at the very heart of the relationship between the knower and the known. It is the containment riddle where, in a universe, is the cosmologist who is studying that universe. This is not a trivial semantic puzzle. It is a deep, epistemological problem that challenges the very foundations of our scientific worldview. All other scientists can, to some extent, avoid this riddle. The biologist studies an organism, but she is not that organism. The geologist studies a rock, but he is not that rock. They can maintain a sense of objective distance, of an observer who is separate from the system being observed, but the cosmologist studies the entire universe, and she is undeniably a part of that universe. She is a product of the very cosmic evolution she seeks to understand. Her consciousness, her thoughts, her theories, are all phenomena within the universe. How, then, can a part contain a picture of the whole that includes the part itself? This is a problem that has been recognized by thinkers for centuries. The philosopher and scientist Erwin Schrödinger, in his book Mind and Matter, pointed to this fundamental paradox. He noted that in order to create an objective, scientific picture of the world, we have, by necessity, excluded the subject of cognition from the domain of nature we seek to understand. We have stepped back and adopted the role of a non-concerned observer, and in doing so, we have created an objective world that does not, and cannot, contain the very consciousness that is doing the observing. The physical universe of our scientific theories contains our physical bodies, our brains, our neurons, but it does not contain our minds, our subjective experience, our awareness. The physical world of atoms and galaxies, governed by mathematical laws, is a brilliant and powerful construction, but it is a construction that is, by its very nature, incomplete. It is a map that does not contain the mapmaker. The containment riddle is a direct challenge to the philosophy of physicalism or materialism, the idea that life and mind are nothing more than the collective dance of atoms, that consciousness is fully contained within, and can be fully explained by, the physical universe. Those who hold this view often confuse the physical universe, which is a scientific model, a world picture, with the unknown universe, the totality of reality, which includes the mind that creates the picture. They mistake the mask for the face. The riddle forces us to confront the possibility that consciousness is not a phenomenon in the universe, but is, in some sense, co-extensive with it, or even primary to it. This is not to deny the immense success of the physical sciences. The physical universe is a powerful and useful model that allows us to understand how things work and to control our environment. But it is a model, an image, a story, and the storyteller, the image maker. The consciousness that weaves the facts and spins the ideas is not contained within the story. The answer to the containment riddle, then, is that we, the conscious, observing beings who create these universes of thought, do not live in our models. We live in the larger, unknown universe, the totality that includes both the physical world and the mind that knows it. Our scientific and philosophical models are our attempts to create a map of this territory, but the map can never be the territory itself. The physical universe contains the brain, but it is the mind that contains the physical universe. This is a subtle but profound shift in perspective. It suggests that an adequate cosmology, a true theory of everything, will not be complete until it can account for the existence of the cosmologist herself. It will require a new kind of science, a science that can bridge the gap between the third-person, objective description of the physical world and the first-person, subjective reality of conscious experience. It is a challenge that has haunted philosophy in various guises for centuries. From the self-referential paradoxes of epistemology to the dizzying, bottomless chasm of self-awareness described by the Danish student in Paul Müller's famous tale. And it is a challenge that now, in the age of modern cosmology, stares the physicist directly in the face. We are not just in the universe is in us. And any final theory that fails to account for this fundamental, paradoxical, and beautiful truth will be, at best, a brilliant, but ultimately incomplete, picture of reality. The physical universe, as described by our scientific theories, is a world of matter, energy, and natural laws. But what, precisely, is a natural law? Are the principles that govern the evolution of life, for example, as fundamental as the laws that govern the motion of the planets? Since the time of Charles Darwin, the theory of evolution by natural selection has been the cornerstone of modern biology. And yet, it has often been challenged as being unfounded speculation, a historical narrative that cannot be proven with the same rigor as a physical law like gravity. But this is a profound misunderstanding of the nature of science. The law of natural selection is as physical, as real, and as demonstrable as any other principle in science. The theory requires just three simple and observable components. First, an interbreeding population of organisms. Second, a source of variation among the members of that population, which we now know to be rooted in the random mutations of their genetic code. And third, a selective environment, a set of conditions that causes differential survival and reproduction. Those organisms whose variations happen to give them a slight advantage in a particular environment will be more likely to survive and to pass on their genes to the next generation. Over time, these advantageous traits will become more common in the population, and the species will change. It will adapt. It will evolve. This is not a speculation. It is a logical necessity. And we have overwhelming evidence for its effectiveness, not just in the fossil record, but in our everyday lives. The widespread use of antibiotics, for example, has created a powerful selective environment for bacteria. Those rare individual bacteria that happen to have a random mutation that confers resistance to an antibiotic will survive and reproduce, while their non-resistant cousins are wiped out. The result is the evolution of antibiotic-resistant superbugs, a direct and often dangerous demonstration of natural selection in action. The law of natural selection is a beautiful example of how simple, local, and random processes can, over time, give rise to immense complexity, order, and adaptation. It is a law that connects the microscopic world of genes to the macroscopic world of organisms and ecosystems. And it is a law that is deeply intertwined with the arrow of time. Evolution is a historical process, a one-way journey of increasing adaptation and complexity, a process that is only possible in a universe with a strong thermodynamic arrow of time. But is life itself, the very phenomenon that natural selection acts upon, something that is fully contained within the physical universe? This brings us back to the containment riddle. The biologists will tell us that life is a manifestation of complex, organized physical systems of cells and atoms. But this is a description of the how of life, not the what of life. It describes the physical vehicle, but not the subjective experience of being alive. The physical universe contains the physical representations of life, the wild flowers, the brains, the DNA. But does it contain the aliveness itself? The mystery of life, like the mystery of consciousness, seems to point to a reality that is not fully captured by our current physical models. It hints at a universe where the distinction between the living and the non-living, between the mental and the material, may not be as absolute as we assume. The law of natural selection is a physical law that operates on living systems, but the very existence of those living systems, with their strange and wonderful properties of self-organization, of metabolism, of awareness, remains one of the deepest and most beautiful mysteries of the cosmos. The boundaries of our universe, both in time and in space, pose some of the most profound and challenging questions in all of cosmology. We have spoken of the cosmic horizon, the limit of our observable universe. But what about the edges of time itself? A Big Bang universe, in its standard form, has a definite beginning, a time-like edge in the past. If this universe is destined to collapse back on itself in a big crunch, it will have two time-like edges, a beginning and an end. What is the nature of these cosmic boundaries? They are presumably not sharp, cliff-like edges, but are more likely to be regions where the very concepts of space and time, as we know them, break down. The orderly historical sequence of events that constitutes our classical, macroscopic world may dissolve into a chaotic, quantum, metrical foam at the beginning and the end of time. The truth is, we do not fully understand these time-like edges, perhaps because we do not fully understand the nature of time itself. Insofar as time is a physical dimension, a part of the physical universe, it seems logical to assume that it is contained within the universe and cannot extend outside of it. The question, what came before the Big Bang, is often dismissed as being meaningless, as before is a concept that requires the existence of time. But this is not necessarily the end of the story. There are ways in which we can talk sensibly about a before. If our universe is just one bubble in a larger, eternally inflating multiverse, then before our Big Bang, there was the inflating quantum vacuum of the meta-universe. If our universe is part of a cyclic model, then before our Big Bang, there was the contracting phase of a previous cosmic eon. And there is another, even more intriguing possibility, the idea of contained creation within a parent universe. Suppose that our universe is the offspring of another, pre-existing physical universe, reproduced either spontaneously through a quantum process, like the formation of a black hole, or perhaps, even more speculatively, deliberately, by a highly advanced intelligent life in the parent universe. In this scenario, we can meaningfully speak of what happened in the parent universe before the birth of our own. The physicist Joe Rosen has even shown that it is theoretically possible for such a system to be self-creating, a cosmic Ouroboros where Universe X creates Universe Y in its own time, and Universe Y in turn creates Universe X in its time. This distinguishes between contained creation, which is the emergence of a new thing at a specific time and place within a pre-existing space like the birth of a flower or a child, and uncontained creation, which is the timeless and placeless creation of the universe itself. The popular conception of the creation of the universe often mistakenly frames it as a contained creation, an event happening in a pre-existing void, which leads to the misguided question of what came before. A more sophisticated understanding sees the creation of the universe as an uncontained one, an event that brings time and space themselves into being. But the possibility of a parent universe reframes the question once again, suggesting that our universe's creation may have been a contained event within a larger, pre-existing reality. This is a concept that blurs the line between science, philosophy, and even theology. It is a testament to the fact that as our scientific understanding deepens, the questions we ask become more profound, more subtle, and more beautifully intertwined with the great, timeless mysteries of existence. The quest to build an adequate cosmology, a complete and satisfying picture of the universe, is inextricably linked to the quest to build an adequate philosophy of mind. The two are not separate endeavors, they are two sides of the same deep inquiry into the nature of reality. As the philosopher of science Edwin Burt wrote, a truly adequate cosmology will only be possible when we have a philosophy of mind that can satisfy both the behaviorist impulse to make the mind a material for experimental manipulation and exact measurement, and the idealist impulse to account for the startling difference between a universe without mind and a universe organized into a living, sensitive unity through mind. The human sciences, from psychology to sociology, currently face an impasse precisely because their central concept, the self, remains a deeply mysterious and transcendental entity, a concept that resists a purely materialistic explanation. At the roots of all our knowledge, from the most objective physics to the most subjective psychology, lies the containment riddle. This riddle, in its various guises, has haunted Western philosophy for centuries, and now it has come to haunt the foundations of physics itself. It is the riddle of the self-referential loop, of the system that tries to contain a complete description of itself. The physicist Leon Rosenfeld, a close collaborator of Niels Bohr, recounted how Bohr himself was deeply impressed by this problem, as it was expressed in Paul Müller's The Tale of a Danish Student. The student in the tale is tormented by epistemological paradoxes, by the fact that his mind divides itself into two persons, one who tries to fool the other, while a third, who is in fact the same as the other two, is filled with wonder at this confrontation. "I don't know which ego is the real one to stop at," the student laments, "for as soon as I stop at any of them, another ego stops at it. My head gets all in a whirl with dizziness as if I were peering down a bottomless chasm, and the end of my thinking is a horrible headache." This is the infinite regress of self-awareness, the mind that tries to observe itself, observing itself. It is the same infinite regress that confronts the painter who tries to paint a picture of his studio that includes himself painting the picture. And it is the same infinite regress that confronts the cosmologist who tries to create a physical model of the universe that includes the very consciousness that is creating the model. Erwin Schrödinger recognized this problem with profound clarity. "Without being aware of it," he wrote, "we exclude the subject of cognition from the domain of nature that we endeavor to understand. We step with our own person back into the part of an onlooker who does not belong to the world, which by this very process becomes an objective world." And this act of exclusion, this strategic stepping back, is what has allowed for the immense success of the objective, third-person perspective of science. But it is a success that has been achieved, as Schrödinger noted, at the high price of taking ourselves out of the picture. A complete and satisfying picture of the world, he argued, must somehow find a way to put the observer back in. The containment riddle is not just a puzzle for physicists and philosophers, it is a deep, existential reality that we all live with. We are both the subjects and the objects of our own experience. We are both the dreamer and the dream. And any final theory of reality that fails to embrace and account for this fundamental, paradoxical, and beautiful duality will be, at best, a partial and incomplete truth. The concept of a final theory, a single, complete, and consistent set of principles that would explain all the phenomena of the physical world, has been a powerful and enduring dream in the history of physics. The physicist Steven Weinberg, in his book, Dreams of a Final Theory, eloquently expressed this hope. Our present theories are of limited validity, still tentative and incomplete, but behind them now and then, we catch glimpses of a final theory, one that would be of unlimited validity and entirely satisfying in its completeness and consistency. String theory, with its potential to unify gravity and quantum mechanics, is often held up as the leading candidate for such a final theory. But is the quest for a final theory a realistic one, or is it a modern scientific version of an ancient religious quest for absolute truth against this modern dream of finality? We can contrast the medieval principle of learned ignorance, most famously articulated by the 15th century cardinal and philosopher Nicholas of Cusa. Cusa argued that the true path to wisdom lies not in the accumulation of knowledge, but in the growing awareness of our own ignorance. The more we know, the more we become aware of the vast, uncharted territory of what we do not know. This is not the simple, unlearned ignorance of the unaware, but a profound, learned ignorance, an enlightened state of humility and wonder. No man, Cusa wrote, can progress farther along the road to perfection than the point where he is found most knowing in the very ignorance that characterizes him. This is a perspective that resonates deeply with the current state of fundamental physics. Every major discovery, from relativity and quantum mechanics to dark matter and dark energy, has not led to a final, complete picture, but has opened up new, deeper, and more profound questions. The circle of our knowledge expands, but the circumference of our ignorance, the boundary with the unknown, grows with it. This suggests that the universe may be, in its very nature, inexhaustible. There may be no final theory, no bottom to the cosmic rabbit hole. Reality may be a series of nested, and perhaps infinite, layers of complexity and mystery. This is a humbling, but also deeply exciting, prospect. It means that the human adventure of scientific discovery will never be over. There will always be new horizons to explore, new puzzles to solve, new wonders to uncover. The quest for a final theory may be a necessary and powerful motivator for scientific progress, a guiding star that pulls us forward into the unknown. But perhaps the true wisdom lies not in the hope of one day arriving at a final destination, but in the journey itself, in the process of constantly expanding our knowledge and, in doing so, deepening our appreciation for the beautiful, infinite, and ultimately unknowable mystery of the cosmos. The choice between the dream of a final theory and the wisdom of learned ignorance is a choice between two different postures towards the universe, one of mastery and one of mystery. And perhaps a truly mature science, like a truly mature human being, will be one that can hold both. The very concept of space, which seems so simple and intuitive to us, has been the subject of a long and complex historical evolution, a journey that mirrors the development of our scientific and philosophical understanding of the world. From the heroic age of Greece until modern times, we can trace the development of two competing views, dressed space and undressed space. The idea of undressed space of a pure, empty void that exists in its own right, independent of the things it contains, was initially a radical and difficult abstraction. It was the view of the ancient Greek atomists, like Leucippus and Democritus, who proposed that reality consisted of nothing more than atoms moving in an infinite void. But for many, including the great philosopher Aristotle, this idea was nonsensical. A vacuum is nothing, he argued, and what is nothing does not exist. For Aristotle, space was always dressed, always filled with some kind of substance. He believed in a finite universe, with the Earth at its center, surrounded by a series of celestial spheres made of a fifth element, the ether, Beyond the outermost sphere of the fixed stars, there could be no space, because there was no matter, no ether, to fill it. This Aristotelian view of a dressed, finite space held sway for centuries. Medieval scholars, while grappling with the theological implications, eventually found a way to extend space beyond the sphere of the stars by inhabiting it with the omnipresence of God. But the idea of a true material vacuum remained a philosophical impossibility. In the 17th century, the French philosopher and scientist René Descartes also advocated for a form of dressed space. For him, the very definition of matter was extension, and so wherever there was space, there had to be matter. His universe was a plenum, a continuous, infinitely extended substance, with no possibility of a void. But the tide began to turn with the rise of experimental science. The invention of the air pump in the 17th century allowed scientists like Robert Boyle to create what appeared to be a vacuum in the laboratory, challenging the long-held Aristotelian and Cartesian views. This experimental evidence, combined with the immense theoretical success of Isaac Newton's physics, which was built on the concept of absolute, undressed space, led to the triumph of the Newtonian worldview. For the Newtonians, space was an infinite, eternal, and absolute container, a fixed stage upon which the drama of particles and forces played out. But the idea of a dressed space did not die. The discovery in the 19th century that light is an electromagnetic wave traveling at a finite speed raised a new question: what is the medium that is waving? Just as sound waves need a medium like air to travel, it was thought that light waves must need a medium to propagate through the vacuum of space. And so, physicists resurrected the idea of the ether, this time a luminiferous ether, a subtle, all-pervading substance that filled all of space and acted as the carrier for light. The advent of Einstein's special theory of relativity in 1905 finally did away with the need for an ether. Einstein showed that the speed of light is a universal constant, the same for all observers, and that the laws of electromagnetism do not require a special, privileged reference frame, which the ether would have provided. The undressed space of the atomists and Newton was reinstated, now unified with time, into the four-dimensional continuum of space-time. But the story does not end there. With Einstein's general theory of relativity in 1916, space-time was dressed once again, but in a new and far more profound way. Space-time was no longer a passive, static background, but a dynamic, physical entity, its geometry curved and warped by the presence of matter and energy. And as we have seen, the development of quantum field theory in the 20th century has given space-time its final and most mysterious dressing: the zero-point energy of the quantum vacuum, the seething, energetic sea of virtual particles that fills every corner of the cosmos. The history of our concept of space is a beautiful, dialectical dance between the abstract and the concrete, between the void and the plenum, between emptiness and fullness. And what we have arrived at today is a vision that, in a sense, unifies these two ancient ideas. The universe is, at its core, a quantum vacuum, an undressed space in that it is the fundamental ground of being. But this vacuum is not an empty nothingness. It is dressed with a rich, dynamic, and endlessly creative energetic structure, a structure that is the very source of all the matter, all the forces, and all the complexity we see in the world around us. The nature of time, even more so than space, is a subject that has perplexed and fascinated the human mind since the dawn of thought. What, then, is time? Asked the philosopher St. Augustine in the 5th century. If no one asks me, I know what it is. If I wish to explain what it is to him who asks me, I do not know. These words still resonate with us today, capturing the deep, intuitive familiarity, and yet profound, conceptual elusiveness of time. We seem to experience time in a way that is fundamentally different from our experience of space. Space is the realm of the objective, the external, the world of things that we can see, touch, and measure with a meter stick. Time, on the other hand, seems to be the realm of the subjective, the internal, the world of our own, flowing stream of consciousness, of sensations, emotions, and ideas. And yet, modern physics has taken this subjective, flowing, and seemingly non-spatial experience of time and has, in a sense, spatialized it. It has stripped away many of the characteristics of the time we experience in our everyday lives, its flow, its transience, its division into a past, present, and future, and has made it akin to a dimension of space. Our physical world in the modern relativistic picture is a four-dimensional space-time continuum, a unified block of reality that contains all of space and all of time. This concept, which had its roots in the work of 19th century mathematicians and thinkers like Charles Hinton, was given its definitive form by Hermann Minkowski in the wake of Einstein's special theory of relativity. In a space-time diagram, the history of an object is represented by a world line, a line that traces its path through the four-dimensional continuum. A point on this diagram is an event, a specific location in space at a specific moment in time. The profound and unsettling consequence of this picture is that, in a very real sense, nothing ever happens in the space-time block. The entire history of the universe, past, present, and future, is laid out once and for all in a single, timeless, four-dimensional geometry. The restlessness of the world, its constant state of change and becoming, has been tamed, frozen into a static, eternal landscape. The philosopher William James dubbed this the block universe, a concept that does away with the very notion of a flowing now. In a tenseless four-dimensional world, it is wrong to say that one event has happened, another is happening, and a third will happen. All events are simply there, at their specific coordinates in the space-time block. An object does not move along its world line from the past to the future. It simply exists at all the points along its world line simultaneously. The feeling of the flow of time, the sense of a moving now that separates a fixed past from an open future, is, in this view, a subjective illusion of our own consciousness. As the physicist Hermann Weyl wrote, "The objective world simply is. It does not happen, only to the gaze of my consciousness. Crawling upward along the lifeline of my body, does a section of this world come to life as a fleeting image in space which continually changes." This is a powerful and elegant picture, but it is one that comes at a high price. It leaves us with a deep and seemingly unbridgeable gap between the timeless, static, and objective world of physics and the transient, flowing, and subjective world of our own lived experience. The problem of transience, of how to account for our powerful and undeniable experience of a moving now, is one that physicists tend to dismiss as a psychological or metaphysical issue, not a physical one. But as the philosopher Gerald Whitrow pointedly asked, how do we get the illusion of time's transience without presupposing transient time as its origin? How can a world in which nothing ever changes give rise to an experience of constant change? This is the paradox that lies at the heart of our modern understanding of time. If the now is moving up our world line, at what speed is it moving? This question forces us to invoke a second dimension of time, and then a third, leading to the absurdity of an infinite, serial time. The spatialization of time, while a powerful and necessary tool for physics, seems to have left out the very essence of what time is for us, as conscious, living beings. The real problem, perhaps, is that we have tried to fit our rich subjective experience of time into a purely objective physical model. And in doing so, we have, as Schrödinger noted, taken ourselves out of the picture. A complete understanding of time may require a new kind of physics, a new kind of philosophy, one that can bridge the gap between the block universe and the flowing river, between the is of physics and the becomes of our own conscious experience. The puzzle of the arrow of time, the fact that the macroscopic world of our experience has a clear and unambiguous direction from past to future, is made even deeper by the fact that the fundamental laws of physics that govern the microscopic world are, for the most part, time reversible. The equations of motion for a single particle, the laws of electromagnetism, the Schrödinger equation of quantum mechanics, all of these work just as well for a movie played in reverse. And yet, the collective behavior of a large number of particles is clearly not time reversible. A mug of coffee on your desk will always cool down. It will never spontaneously heat up by drawing heat from the surrounding air. The flow of heat from hotter regions to cooler regions is a one-way street, a process governed by the second law of thermodynamics, the law of increasing entropy. This law provides the thermodynamic arrow of time. It seems that the arrow of time is an emergent phenomenon, something that arises from the collective, statistical behavior of many particles, but is not present in the laws that govern the individual particles themselves. It is like looking at a painting. If you look at a single dab of paint up close, you cannot tell which way is up. You have to stand back and look at the large-scale arrangement of many dabs of paint to see the picture and to know which way to hang it. In the same way, the arrow of time is not found in the microscopic details, but in the macroscopic patterns of the universe. We can visualize this in a space-time diagram. The world line of a single isolated particle has no inherent direction, but the world lines of the many particles that make up a hot cup of coffee are highly agitated. They are crinkled. And as time progresses, as we move up the diagram, this crinkledness, this agitation, spreads out to the neighboring, less agitated world lines of the surrounding air through collisions and other interactions. The system as a whole becomes more disordered, more crinkled on a larger scale. This process is not time reversible. If you were to turn the space-time diagram upside down, you would see agitation spontaneously concentrating from the cool air into the hot coffee, a clear violation of the second law. But this explanation just pushes the question back to the initial conditions of the universe. The second law only works because the universe started in a state of incredibly low entropy, a state of high order. The universe began with all its world lines in a very smooth, uncrinkled state, and the arrow of time is simply the story of the universe's long, slow, and inexorable journey towards a more crinkled, more disordered, and more probable state. Another, related, arrow of time is the electromagnetic or radiative arrow. The equations of electromagnetism are time reversible. They allow for both retarded solutions, where waves radiate outwards from a source into the future, and advanced solutions, where waves converge inwards onto a source from the past. In our universe, we only ever observe retarded waves. A light bulb emits light outwards. It never absorbs light inwards from all directions to become unlit. This is another fundamental asymmetry of our world, and it is also thought to be a consequence of the low entropy initial conditions of the universe. The cosmological arrow of time is the direction of the universe's expansion. The physicist Thomas Gold argued that this is the master arrow, that the future is, by definition, the direction in which the universe is expanding. This provides a clear directionality, but it raises the question of what would happen if the universe were to one day stop expanding and begin to contract. Would the arrow of time reverse? Would entropy start to decrease? Would people start to grow younger? This is a fascinating, if highly speculative, question. The current consensus is that the thermodynamic arrow of time would likely not reverse in a contracting universe. The processes that generate entropy are local and do not depend on the overall expansion or contraction of the cosmos. A contracting universe would likely continue its journey towards a state of higher entropy, culminating in a hot, dense, and highly disordered Big Crunch. All of these different arrows of time, the thermodynamic, the radiative, the cosmological, and the psychological arrow of our own memory, seem to point in the same direction in our universe. And they all seem to be rooted in the same, deep, and unexplained mystery, the incredibly special, low entropy state of the early universe. The arrow of time is not just a feature of physics, it is the very framework of our existence, the condition that makes life, memory, and causality possible. And the fact that this most fundamental feature of our reality is still not fully understood is a profound testament to the deep and enduring mysteries that lie at the heart of the cosmos. The basic parameters of our physical world, the fundamental constants of nature, seem, on the face of it, to be arbitrary and accidental. There is nothing in our current theories that explains why the speed of light has the value it does, or why the charge of the electron is what it is. They are numbers that we must measure experimentally and then plug into our equations. And yet, as we have seen, These numbers appear to be exquisitely fine-tuned to allow for the existence of a complex, life-bearing universe. This is the fine-tuning problem, and it presents us with a stark choice between two very different philosophical pictures of the cosmos. The first picture is the one offered by the anthropic principle in the context of a multiverse. In this view, our universe is just one of a vast, and possibly infinite, ensemble of other universes, each with its own, randomly assigned set of physical constants. The constants in our universe are accidental in that they are just one random draw from a vast lottery of possibilities. The reason we find ourselves in a universe with life-friendly constants is simply a matter of selection bias. We could not have found ourselves in any of the other, far more numerous, sterile universes. This is a powerful and scientifically respectable explanation, but it is one that many find to be philosophically unsatisfying, as it relies on the existence of an infinite number of unobservable realities and abandons the hope of a deeper, more fundamental explanation for the properties of our own. The second picture is the one offered by the bootstrap hypothesis. In this view, the universe is a single, unique, and completely self-consistent whole. There are no accidental or arbitrary features of a fundamental nature. The values of the constants, the properties of the particles, the very laws of physics themselves are not random draws from a cosmic lottery, but are all fixed and uniquely determined by the requirement of overall mathematical and logical consistency. The universe is the way it is because it is the only way it could be. It pulls itself up by its own bootstraps. This is a much more aesthetically and philosophically appealing vision for many physicists. It is the dream of a final theory, a theory of everything that would have no free parameters, a theory from which all the properties of our universe could be derived from first principles. This was the dream that drove Einstein in his later years, and it is the dream that still motivates the search for a unified theory like string theory. In the bootstrap picture, the universe is not a random accident, but a mathematical necessity. In the absence of such a final bootstrap theory, the anthropic principle can be seen as a kind of makeshift or poor man's bootstrap. It is a way of establishing a relationship of self-consistency, not at the level of fundamental laws, but at the level of existence itself. It relates the properties of the universe to the existence of the organisms that observe it. When we observe a living organism, a wild flower, or a human being, we are also, implicitly, observing the universe that was capable of producing it, a universe with the right chemistry, the right stellar evolution, the right physical constants. The organism and its universe form a self-consistent, if partial, bootstrap loop. The ultimate hope of the bootstrap dream is that one day, our understanding will be so complete that we will be able to deduce the entire structure of the universe from the properties of a single, fundamental particle, like an electron. We will see, as the poet William Blake envisioned, a world in a grain of sand and a heaven in a wild flower. We will understand that the electron has the properties it does because it is part of a self-consistent whole, and that the universe has the properties it does because it is the only one that can contain a self-consistent electron. This is a vision of a universe that is not just a collection of contingent facts, but a deep, interconnected, and logically necessary unity. The choice between these two pictures, between the multiverse of chance and the bootstrap of necessity, is one of the central, unresolved tensions in modern fundamental physics. It is a choice that is not just about science, but about our deepest philosophical intuitions about the nature of reality. And it is a choice that may not be resolved until we have a final, complete theory of quantum gravity. A theory that can tell us whether our universe is a unique mathematical masterpiece, or just one beautiful, and very lucky, ticket in an infinite cosmic lottery. The quest to build a complete and satisfying picture of the universe, a cosmology that can account for all the phenomena of nature, is a journey that has led us to the very limits of our understanding, to the frontiers of space, of time, and of knowledge itself. We have traveled from the quantum foam of the primordial void to the eternal, self-reproducing landscape of the multiverse. We have explored the fiery crucible of the Big Bang, the strange, repulsive power of dark energy, and the deep, enduring mystery of the arrow of time. We have grappled with the paradoxes of quantum mechanics, the riddles of extra dimensions, and the profound philosophical implications of the anthropic principle. And in this grand intellectual adventure, we have been forced again and again to confront the limitations of our own human perspective. The containment riddle, the paradox of the observer who is part of the system being observed, is a stark and humbling reminder that any picture we create of the universe will be, by its very nature, incomplete. We are the mapmakers who are trying to draw a map of a territory that includes the mapmaker himself. This is a logical and epistemological puzzle that may never be fully resolved. It suggests that a final, objective, God's eye view of reality may be forever beyond our reach. The universe we know, the universe we study, is a participatory universe, a reality that is co-created in the dialogue between the cosmos and the consciousness that seeks to understand it. This does not mean that science is a purely subjective enterprise. The physical universe, as described by our scientific theories, is a powerful and remarkably successful model. It has allowed us to understand the workings of nature with incredible precision, to control our environment, and to create the technologies that have transformed our world. But it is a model, a map, a story. And it is a story that is, at present, profoundly incomplete. It has a gaping hole at its very center, the mystery of life and mind. Our physical theories can describe the dance of the atoms that make up a brain, but they cannot explain the subjective experience of consciousness that arises from that dance. They can describe the chemical processes of a living cell, but they cannot capture the emergent, holistic property of aliveness itself. The person who persistently asks, "Where is life in the physical world?" is passed from biologist to psychologist to physicist, each discipline admitting, in its own way, the limits of its own perspective. The buck, as the saying goes, stops with the cosmologist, because the cosmologist is the one who claims to study the whole thing. But the cosmologist, too, must confess a deep and profound ignorance. A truly adequate cosmology, as the philosopher Edwin Burt noted, will not be possible until we have an adequate philosophy of mind, one that can do justice to both the physical and the mental, the objective and the subjective, the outer and the inner aspects of our reality. The journey to understand the origin of the universe is, in the end, a journey to understand ourselves. We are not separate from the cosmos. We are a part of it. We are the universe's way of becoming aware of itself. The atoms in our bodies were forged in the fiery hearts of long-dead stars. The consciousness that is listening to these words is a product of a 14 billion year long cosmic evolutionary process. And the questions we ask about the universe, its origin, its nature, its destiny are the universe's own questions, asked through us. This is a vision of our place in the cosmos that is both profoundly humbling and deeply empowering. It is humbling because it reminds us of our finitude, of the vastness of our ignorance, of the deep and enduring mysteries that will likely always lie beyond our grasp. But it is also empowering because it places us, as conscious, questioning beings, at the very heart of the cosmic story. We are not just insignificant specks of dust in a cold, meaningless void. We are the meaning makers, the storytellers, the observers through whom the universe comes to know and to wonder at its own magnificent existence. And as you lie on the threshold of sleep, as your own individual consciousness prepares to dissolve into the vast, mysterious, and creative ocean of the unconscious, you can feel a sense of participation in this grand, cosmic adventure. The journey is far from over. The greatest discoveries, the most profound insights, may still lie ahead. But the quest itself, the shared human endeavor to understand our cosmic home, is a journey that gives our fleeting lives a meaning and a dignity that can rival the stars themselves.